having this. I exactly realized.
Oh, actually, we need your mic.
Oh, wow.
Yes.
Second, they want to making this the market is not this. But by the way, I hear a lot of people don't come to the market because of the weather, which is kind of funny. In retrospect, amazing.
Repeat the jokes.
That much traction, so there's no
You know. Okay, thank you. Okay, so what I want to talk today about is 2 sessions of 15 minutes each. So I'm going to assume complete knowledge with both twisted bilayer graphene and fractional churn insulators. The work was, obviously done by a group of fantastic people, starting with Dumitru, Jonah, Hayu, Jabin, Jida, and all this group of people on the twisted bilayer graphene side. And on the FCI side, Jabin, Jonah, Yves Kwan, and of course, my long-term collaborator, Nicola Arnio. Now, as I said, I assume full knowledge of twisted bilayer graphene. Happening. So basically, the band structure of twisted bilayer graphene at the magic angle is that of 8 for 2 per valley per spin, so 4 times 2 determinacy. Flat bands or almost flat bands, where you can fill them from -4 electrons to 4 electrons. Now, of course, this would be a metal, but everybody knows what we see in experiments are a bunch of insulators and superconductors. So clearly, many body effects are crucial. Now, if you go a little bit deeper into experiments, you've got a conundrum that you need to explain. There's a lot of experiments that basically suggest the presence of localized moments. And here we talk about entropy experiments, compressibility experiments, and most of all, STM experiments that basically see what I'm not sure how you can explain it otherwise. Hubbard bands, I guess you could explain with Van Hoff singularities also, but there's clear hints of localized behavior, and of course we see hints of delocalized behavior too. I guess not hints, but clear proof of delocalized behavior in such a way that Shahalilani and Pablo Herrero basically said in their abstract of one of their papers that the correlated state features unusual combination of seemingly contradictory properties, some associated with itinerant electrons and others associated with localized moments. So how do we explain this duality of the twisted bilayer bands? Well, it turns out there's an easy way to do it. If you try to think of the flat bands as made out of localized orbitals. Now, there's a problem with that because you can't, a priori do this because the representation of the bands at the gamma point clearly tell you that the bands cannot be localized. So these bands are topological. It's a special type of topology, and the topology happens by basically sort of band inversion at the gamma point. I don't have time to go into the full details. The statement is not fully correct, but the gamma point is the culprit. But everywhere else, you can see there's a large gap to the dispersive bands, and everywhere else, the bands turns out can be localized by basically putting an electron, or actually 2 electrons, on the triangular sides of the Moire lattice. You put 2 electrons, px plus minus ipy. We're going to call them f electrons by abuse of language. At the triangular sites, you find out that more than 95% of these bands, the weight is in these f electrons. And basically, the only problem is the gamma point, where the f electrons, being an atomic limit, have 0 overlap with the actual TBG bands. But what you can do is basically pawn off the topology onto a topological semi-metal, which is looks like untwisted AB bilayer graphene. You can see the double Dirac vortex here, which basically carries the topology of the bands. And think of the system as, this is not just a picture, you can actually derive this from first principles, if you want to, which we did. You can think of the system as localized F electrons on the triangular side, exactly where the FDM sees the charge localization, and then delocalized or itinerant electrons that basically have this double vortex that look like untwisted bilayer graphene. So the F electrons carry the flatness, the C electrons carry the topology, and the Hamiltonian becomes really simple in this case. This is basically a unitary transformation that it's a faithful representation of all the symmetries of the Bistrom-McDonald model. And you make a unitary transformation, and you find out that the Hamiltonian basically looks like this. In the F sector, the Hamiltonian is 0 because these localized F orbitals, they are localized on point 2, the Moire unit cell. They don't basically talk to each other. The Hamiltonian is 0. Now, in the C sector, you find the Hamiltonian of bilayer graphene, basically, which is that of a double vortex here. This Dirac Hamiltonian here are actually going to give you a double vortex with a mass. And this mass here is basically the difference between these levels and would give you the Bistrom-McDonald bandwidth. Now, you add a coupling between the F and the C electrons, which is gamma, which basically is the gap between the flat bands and the remote bands. Now, I warn you that the remote bands in STM are basically within the Hubbard U, so it's not, they should be considered. And then you get this matching of the Bistrom-McDonald model to this level. The red dots are the Bistrom-McDonald model, the black lines are this model. So the matching is quite amazingly good at single particle level. And what I want to argue, what we want to argue basically, is that whenever you have band inversion causing topology, so whenever the remote bands are not flat themselves, they have a dispersion. This is kind of a generic mapping into heavy fermions. Why? Well, Dumitru, Jabin, Jonah, and Hoyu basically showed that if you've got band inversion at some spots in the Brillouin zone, then the Berry curvature will be localized at those points. And by Berry curvature, we mean non-abelian one also, because twisted bilayer has 0 active Berry curvature, but has non-abelian one. So away from these hotspots where the topology, where the band inversion had occurred, you have no Berry phase, and then you can localize basically and form finding orbitals everywhere in the Brillouin zone almost, but not at the point where you had the band inversion if the flat bands are topological. But what you can do is pawn off the topology onto a topological semi-metal or topological metal or metal, and describe the system as localized orbitals coupled to a topological semi-metal, like in twisted bilayer. And then the localized orbitals, the good thing about this basis is that the localized orbitals will carry the interaction. You basically made a unitary transformation to a problem that is now local. Now,
So Andrei,
yes.
a question.
Okay.
You said when you have topology from band inversion, then this is the case. Can you give examples where topology comes otherwise?
Yeah, so basically, for example, in twisted bilayer doesn't really come from band inversion. It's a continuum model. You're always going to get topology, actually. And but the more generic examples are tri-layers, for example, where you get stacking, anyways, reconstruction and stacking, and then the I think there's several papers in the field, including Valentin's, but basically what happens in that case is the remote band is also kind of flat. So you don't have hotspots in the where so if your band looks like a lambda level, you're not going to be able to make this mapping. But if your band has localized curvature, which in all band inversion system it does, then you're going to be able to make this mapping. Very good. Thank you for the question. Okay, so then I argued that this mapping basically gives you the relevant interacting degrees of freedom, and the interacting Hamiltonian, which can also be derived, everything here is derived, not postulated, has the following form. It has Hubbard interaction, but the Hubbard interaction is between the F electrons. Okay, and this U is the largest energy scale in the problem. It's larger, about 3 times larger than the hybridization between the F and C electrons. It's got some Coulomb between F and C electrons, density factors, which are actually important that the Anderson model does not have. So this is why we call it Anderson plus model. And it's got a ferromagnetic exchange between the F and the C electrons. And these are some U4 spins in, because of a large symmetry group of twisted bilayer. These are some U4 spins of the F and the C electrons. And these will become important. So right now, the F electrons carry the strong correlation set, and the C electrons carry the dispersive bands, and you've got this Hamiltonian. Now, this looks like a complicated Hamiltonian, but actually,
Great.
yes,
Sorry, no.
sorry.
What's the relation between bandwidths for C electrons and U?
The bandwidth for C electrons is infinite because the Bicester-McDonald model, despite early, so if you don't add particle hole symmetry breaking, the Bicester-McDonald model, it's topological at any bandwidth. So it's a continuum model. So topological at any bandwidth. So the C electrons bandwidth is infinite. But basically, what you need is, the relationship, the relevant ratio is this gamma, which is the coupling between the F and C electrons to the Hubbard U. And this is about 1/3. Thank you. That's a very good point. So you cannot write the Bicester-McDonald model on lattice. So the C without, if you don't add strain, etc. So then it's a strong topological system. And so these electrons, the C electrons, are basically have infinite bandwidth. But it's okay, because then, I'm only interested, only this ratio is the relevant thing that you do in, DMST or anything.
Sorry, Andrei, when you say 1/3, is it gamma over U 1/3 or U over gamma? Which one is larger, U or gamma?
Thank God, U is larger. Otherwise, this basis would be useless.
Okay.
And that's a fair point. So, okay, so that's, I'm basically not going to be able to finish, but the fair point is the difference between strong coupling and weak coupling.
Right.
And you can make this mapping, even if gamma over U is 3, but it's going to be useless then. Because, you want to basically polarize the F electron. So we're waiting, obviously, for experiments from, for example, Shahali-Lanis group or Dimafatov, who have this microscope, we can measure the band structure. If the band structure has minimum, as I'll show at the gamma point, then I would say you're in strong coupling. If the band structure has a minimum at the K point, then you're in more weak coupling, and there's many theories. A lot of beautiful work from Andrei and of course also your group that basically can differentiate between those couplings. But that's an experimental question in the end. What I will say is that if the experiments come out that the minimum is at the K point, then you've got a problem, some sort of a problem explaining the STM experiments, because they do see Hubbard bands. So I don't know how to, but I'm completely agnostic about this. It's something that should be solved in experiments. Very good. So this interacting Hamiltonian, which is Anderson Hamiltonian, you can solve it in the zero hybridization limit, where the hybridization between the F and C electrons is 0. Then it's an exactly solvable system, just like the Anderson model, exactly solvable when the hybridization between the F and the C electrons is 0. And what you get is that the filling is governed by the F electrons and integer fillings. Okay, they polarize, form Hubbard bands. And then as you increase the filling, you tend to populate the C electrons because they're almost gapless. They've got a small mass, which is the bandwidth of Bicester-McDonald, but they're almost, you populate in this limit, they're actually gapless. You populate the C electrons, and then as you populate the C electrons, your Fermi level gets to the F electrons. At some point, there's a reorganization between the F and the C electrons here, where we call the mixed valence regime. And then you go to the next filling, where you have another integer filling of the F electrons, and the C electron filling varies. So we're going to call the integer filling the local moment, or the integer and the close the fillings where the F electrons occupation number stays put in this particular exactly solvable zero hybridization model, the local moment region, and the other one, the mixed valence region. Now, you can do a lot of perturbation theory, but the best thing to do is to show you the DMFT done by Rosa, Tim, and Giorgio's group, including with Antoine, basically show you that at integer filling, you've got local moments. But away from integer filling, basically, you have deviations from 1 over T sub stability, strong deviations, and you might have an onset of Kondo behavior at much higher T. It's basically a Kondo model at non-integer fillings. So let's understand the behavior of this model at both integer and non-integer fillings. At integer fillings, it's very easy, and this is the reason why basically, obviously, it's in the eye of the beholder. But I like this description because it tells you how the dispersion of the bands comes of the many body bands, or the many body charge 1 excitation above the many body ground state comes at integer filling. So what you do is you have this in zero hybridization, you have this electron there's a C electron, but then you basically polarize the F electrons because you want to save U. And once you polarize the F electrons and you order them, they're going to create a Hartree-Fock field, and that J term that I said it's a coupling between the U4 moments of the spins of the F and the C electrons will basically open a gap here, and you'll also have level crossings here. So you get naturally to such a band structure, which was obtained in strong coupling studies, but this is a natural way of understanding this. Now, if you go to different fillings, you've got this W term, which was a charge, the density term between the F's and the C electrons, and that basically this term in the U basically shift your Hubbard bands relative to the Dirac node at different fillings than charge neutrality, and then you can immediately see that there's a mass imbalance between, this is filling -1, between -1 plus epsilon and -1 minus epsilon. And this naturally explains the Landau level fan, right, which I always point out from charge neutrality. You've got heavy excitations. As you go towards charge neutrality, you're not going to be able to see the result of the Landau fan. And this continues, mu equals 2, mu equals -3. Now, I will get to basically Steve's state. Now, we all know that these are not the exact states, but basically there's a manifold of low-lying states that this belongs to. And all these states in the low-lying manifold satisfy basically this heavy light duality. Heavy charge carriers at -1, towards charge neutrality, so -1 plus epsilon, and light carriers at -1 minus epsilon. Now, if you want to go away from integer fillings, you can actually get different behavior that's not ordering. And these are calculations done by Dumitru and Hauyu that basically implemented a sort of analytical DMFT. Obviously, we're not DMFT experts, but Dumitru and Hauyu made it such that we were able to actually do this calculation to compute the spectral weight transfer at non-integer fillings. And what happens at non-integer filling, for example, 1.5, you can see that the Hubbard bands are here at high temperature. But then as you lower temperature, there's incoherent excitations forming next to the Fermi level. And then at lower temperature, I wouldn't necessarily trust these scales. But at lower temperature, what you see is the formation of coherent excitations transfer spectral weight from the heavy bands, from the Hubbard bands to the Fermi level, and Kondo coherence developing. Now, en passant, I want to basically say that this is one scenario of explaining the STM experiments, which you can see Hubbard bands. There's a gap here either given by strain, which wasn't yet considered. I'll get to strain later in this model, but there's or alignment with the HBM substrate or some other things. We can also model this gap, as I'll show you very soon. But basically, you can see that there's some excitation. There's some Hubbard bands coming in as you vary the filling, and there's some excitations getting stuck to the Fermi level. So one interpretation, which obviously, again, agnostically needs a lot more experimental confirmation, is that that's a Kondo peak. So the other thing that I think is natural in the natural explanation of this duality between F and C electrons, and that I would love to have a critical conversation about, is the explanation of the thermoelectric effect. And the thermoelectric effect says the following. Basically, you can ask Dumitru and Hauyu, and they will tell you, as they told me, that the Seebeck coefficient is negative for electrons and positive for holes. Okay, so as you go from an insulating integer filling state, as you go from holes to electrons, you should see the Seebeck coefficient going from positive to negative. Instead, Dmitry Eftov's group performs these experiments. I don't have time to go into detail. They're not done at the lowest temperature, actually, because you shine light on it, so the sample, you cannot cool the sample down. But they're done, not at the lowest temperature possible, obviously. But they see only negative Seebeck coefficient, for example, for positive integer for positive filling. So you can see that around filling 1, the Seebeck coefficient is negative, even though you do have an insulating state there. So you go from holes to electrons, you see positive to negative, they see negative Seebeck coefficient. How do you explain it? Well, what we claim, so this is actually theory. This is actually the DMFT approximation done by the ITP approximation done by Dumitru and Haoyu. But basically, what you can understand behind the entire machinery is that this tells you something about the lifetime of the excitations around integer filling. So basically, around integer filling, if I had holes, the insulating state, holes and electrons with the same mass, I see positive peak, negative, positive, negative transition, and the Seebeck coefficient. I only see negative. So then you can ask, well, first thing I want is, we know from many even strong coupling, we can give you a mass asymmetry, not just the heavy Fermion model, but strong coupling. But then mass asymmetry, all it will do, it will change the relative height of these peaks. You'll still get negative here, positive here, and negative here. But you don't see this in you see all negative. So then you also realize that if you have heavy and light electrons, the lifetime of the heavy electrons is very, very short. So if you introduce lifetime, so the heavy electrons have two properties. They're both heavy in terms of mass, but also lifetime short. So you do, what which is self-energy calculations, and you get the lifetime. And if you basically, you get it, and you can get it in a calculation. And if it comes out, of course, it will come out that the lifetime of the electrons is much shorter than that of the light electrons, and then the Seebeck coefficient turns negative completely. So we think that this can explain the experiments, but of course, we would love to hear a vivid critique of these ideas. Okay, so now, because Senthil, yes, very good, thank you.
It's not a vivid critique, but just a question. So the heavy particles that your theory leads to, do I understand correctly that the main evidence for them is that they're not seen?
What do you mean?
I mean, they don't show up.
No, you don't understand correctly. So
Okay, good. Explain to me.
So basically, okay, so the heavy quasi-particles, okay, so basically there's many things there's, for example, the asymmetry of the mass in the Landau fan, right?
No, but the Landau fan is not seen.
No, but the heavy quasi-particles can be seen in STM. They're the Hubbard bands, just like I showed the STM data, right? How will you explain that without Hubbard bands? You can explain with some Van Hoos, but it's not, it's basically I would say the STM experiment to see Hubbard bands both in bilayer and trilayer. And if you let me go to the slide, I'll show you, also Bascones calculations on this. They come out, the spectrum of the STM comes out naturally at higher temperature, and they see Hubbard bands, and these are the F electrons. So you do see them.
Andrei.
Oh yes.
So it's not unusual to see thermoelectric effect of wrong sign in sort of regular metals, and not the one predicted by band curvature, just because it's determined by not density of states, but everything, energy derivative of everything. How and can that trivial
It's not
wrong sign be ruled out here?
No, I mean, yeah, that's a question that I'm going to ask. That's a critical. That's the critical questions that I'm asking to can I rule out everything? No, but what Efetov does see is that this behavior happens over, the wide range. You go through all the insulators. There's not just one insulator, right? So, you couple this with the Hubbard band and you couple this with the light and heavy, which from the Landau fan. Can it be something else? That's rule out everything is a hard thing to do, but you need to explain the Landau fans going away from charge neutrality. So you got a light and heavy component, also compressibility, also show you light and heavy component. Then you need to explain the Hubbard bands and STM. Then you need to explain the CBAC. It becomes like your talk yesterday, right? It becomes harder and harder to argue against. But of course, I would like, if there would be another explanation, I would certainly like to see it because that's how we make progress. Thank you. Okay, so now, as Steve, preempting basically, making an introduction to Steve's talk, basically these samples and have a lot of strain. And 5 minutes. Oh my God. Okay, thank you. Does it take into account the questions? Slowly ask questions of the public. Okay, so the samples are strange. You can see this in STM, and basically you can see that this KBC state is not really the ground state in strange samples, and the KBC is not really the ground state even in non-strange samples. It could be another state. So you can ask, well, can we add strain on it? And of course, actually, Senthil was asking for a long time before while I was giving his talk, that the spectrum is not really particle Hall symmetric. So we decided to take his criticism at face value and try to add particle Hall symmetry and strain to this model. Turns out it's very simple. If you add strain, the only thing that you need to do, and this is again from first principles, is you add a mass in the heavy fermion sector, which splits the heavy fermions. And if you want to add particle Hall symmetry breaking, all you need to do is add a chemical potential. And these are not added by hand; they're calculated from Kang and Vafik models of 30 parameters, which in this basis, in this very efficient basis, come out as only 3 parameters. Okay, so now you can see the match with strain and relaxation of the heavy fermion model is very good, and now we can understand the IKS state at a analytical level. What happens is that strain splits the heavy fermion modes in a single particle level, and then when you split the heavy fermion modes, your one-shot Hartree-Fock ground state is just filling this low energy heavy fermion modes and filling the Dirac double vortex to half filling, and then you run Hartree-Fock. And what you see is that if you don't do any boosting of the valleys, so if you do have Q equals 0, you're going to get a gapless system. So then, if you do some boosting of the valleys, this gapless system, even at this is a zero hybridization between the FNC, basically moves a Dirac node at some energy. And now you asked, in order to basically analytically determine the Q vector that is in the IKS state, the condition is that this Dirac node has moved to a heavy fermion band, so it opens a gap. And this is how you determine the boost vector analytically, and it matches within 85% what the unrestricted Hartree-Fock studies from this remarkable paper also find that this Q wave vector is split 2m/3. And you get, of course, the same spectrum, but this is one-shot Hartree-Fock spectrum that you can understand analytically. Last thing, before I get another 3 minutes to talk about fractional turn insulators, hopefully, last thing is the relaxation. So you see the relaxation creates particle Hall asymmetry, which, as I said, Senthil was pointing out in many of the talks before. So we took this seriously, and we tried to model it. And this is in the heavy fermion model. This is just chemical potential of the F and the C electrons, which are different. It's just very simple term. And then I don't have time to go through it, but what comes out of this is that the correlated states at positive filling are much stronger than the ones at negative filling in terms of the gap, even though the band dispersion at positive, the bare band dispersion is larger at positive filling. So this, I think, can also come out naturally just from one shot Happy-Fock. And hence, I think a lot of these things can come out naturally. There's one last thing that we're trying to develop a theory based on Fernandez's group idea of asymmetric phonons, which is the linear resistivity in these systems that we cannot yet explain within this model, but hopefully we'll be able to explain soon. Now, of course, as I said, it's very good to have a critique, a robust critique of this model and any other model that's proposed. And we're of course available for comments. Now, can we take 3 minutes to how much time?
We'll take 3 minutes.
Okay. So I just wanted to give a quick tour of the FTPI calculations, fractional churn insulator calculations, because of course, they also have to do with twisted samples. These are calculations that, followed the experiments of the Washington group, the Cornell group, which basically see fractional churn insulators at fillings, 2/3, 3/5, etc. But no fractional churn insulator, for example, if 4/3, the magnetization which is needed, these things polarize, they have valley and spin degree of freedom, they polarize. There's no magnetization at filling below 0.4 or below 0.35 and above 4/3. So if and of course the pentalayer system, which I will argue in the last five minutes, it's a totally different beast.
Me too.
In the last 30 seconds. Okay, so basically this has been work done by Jabin, that basically at the initial level we needed a model for the fractional churn insulators, and there were models available in the literature, but these models had different parameters. This is the McDonald model, and it turns out, this is a word of caution, that if you take the McDonald model and fit the parameters of the McDonald model at one angle, and then just twist the McDonald model to obtain the band structure at different angles, that seems to not work. At least compared to DFT. One needs to basically also change the parameters of the model as a function of the angle, do some piezoelectricity. And this was something that was initially pointed out by D. Shao, where you can see that basically there's a huge change in churn numbers of the bands in MOT2, or twisted bands in MOT2. There's a change in churn numbers which does not exist. We just took the McDonald model at one angle and use the same parameters to twist. This does not, these phase transfers do not exist. Now we're confirming, we've confirmed basically this band structure in BFT, but this is one big word of caution in doing this. Now, the other thing that I wanted to point out is that there's a huge amount of band mixing in these systems. For example, if you don't use band mixing, i.e. mixing between the first flat band and the second flat band per valley, you're going to get a large spin gap at 4/3, where the experiment sees no magnetization. So you're going to get magnetized states at 4/3. Now, we showed with Jabin that basically this can be immediately understood by taking into account the lack of magnetization at 4/3 by taking into account band mixing. And this band mixing immediately shows you that while you have a FCI at 2/3 or minus 2/3, your state is not spin polarized at 4/3. You can see the other spin sector. Okay, so now I wanted to basically, in the last 30 seconds, I wanted to basically point out how Pentalay is a totally different beast, and how we should have a very strong discussion about it. How I think that all the calculations that have been done so far in the fractional regime are biased, in the sense that they bias towards the fractional churn insulator. Look at the pentalayer band structure. This is a flat band, okay? It's got degeneracies with this dispersive bands. This is work done by Jabin and Jonah and Yves Kwan soon. Okay, there's degeneracies. There's threefold degeneracies at K, twofold degeneracies at M. Dispersive bands are touching basically the flat band, and we can understand this. Now, there's all kinds of issues about normal ordering, which can give you different things. We won't get into that. But let's say that the most important issues is that this band, the flat band, touches the other bands. Now, what you can do is you can do Hartree-Fock, and this is something that's very easy to do. You can do Hartree-Fock and at filling 1 and split this flat band, and then you're going to get a band of churn number 1. There's some phase transitions from churn number 5 to churn number 1. Doesn't matter. I'm not going to get into details. But this is the Hartree-Fock band that you get at filling 1. Okay, so you can explain the integer churn insulator. As you can see here on the phase diagram, there's a large region, phase diagram of Jabin et al. This large region of this. Now, what you can also do is ask, and this is, I'm sure Senthil will get into it. You can ask whether it's a anomalous Hall crystal, which is basically a fancy name for the Moire not mattering, and the Moire mattering in the same charge dispersion there look the same. But what we propose is that one way to distinguish between them is the neutral spectrum, because one of them will be a Wigner crystal and should have a neutral spectrum that's below any other Goldstone modes, and the other one will have a spectrum that's above. Now, there's many papers, well, not many, there's 4 papers that basically now what they do with different subtraction schemes, they take this nu equals 1 churn band that obtain as nu equals 1, and then they fractionally fill it, and then they present a churn insulator, fractional churn insulator. But this band was obtained as filling 1. Okay, so you can't go and then fractionally fill this, and I think we should have a debate about this, a strong debate about this. Now I can show you what you do get if you bias it. So if you take this churn band that's obtained as filling 1 from Hartree-Fock, then fractionally fill it, you're going to get fractional churn insulator. You can see it clearly here. Okay, but if you actually do the system correctly, which means not bias it, fill this band at filling 1/3 and take into account the gapless states, you don't get a fractional churn insulator. Okay, of course, people can say this is just size issues, but it might be reminiscent of some hidden physics that we haven't thought about. So I want to point out no fractional churn insulator if you actually do it correctly without first computing the filling 1, moving the band down, and then projecting into this band. So with that, I want to thank people for their attention.
So if you add strain or relaxation to displacement field, wouldn't you get a correction to the gamma as well? Because
well, not to, I mean, gamma is the main correction you do, okay, but the main correction is the heavy fermion splitting. So, of course, I didn't have time to go through all of it. You can see that there's corrections here. Okay? But the main effect is just the heavy fermion splitting. Very good, thank you.
Elementary question, since you mentioned Van Hoff one phrase in your talk, what is your opinion best evidence that if you take, say, arbitrary filling, not necessarily integer, that what STMC is really Hubbard bands rather than Van Hoff singularity?
Yeah, no, that's a good question. I mean, well, I would say that the key is basically the STMC is the condo. As you well know, and I would say that you can probably model STM. I'm not sure, I don't want to add words like naturally. And you can certainly, this you just do a calculation, you get it. You can probably, model it with Van Hove. I want to see that calculation, but in the end, I would think a condo peak would be the. So I agree with you.
Senthil?
Yeah, so Andrei, I guess we should have a robust debate on Princeton at some other point. I want to get back to your heavy fermion story on TB.
Oh, okay. But you do agree that there's no churn insulator, fractional churn insulator, right? We have a robust conversation, but the data is the data. Okay.
This requires a longer discussion. Let me ask you about the heavy fermion.
Yeah.
Right. So, so the lack of Landau fan going towards neutrality, or the lack whatever signature Thermopov was saying, I can postulate a really, really simple explanation, which is that there's a first order transition, right, between the correlated insulator and the metallic state that emerges out of neutrality. So then, of course, I'm not going to say anything, the metallic state coming out of neutrality then doesn't know anything about the impending correlated insulator. So that's all I need to do to explain the data, right?
Yeah, you
So
need
how
to
do
do
you
that
build it up?
at every filling, I guess. And the offset is negative at every filling above nu equals 0. So you need to do you need to do this at every filling, and you need to see this in compressibility too, which I guess
The first order transition, yeah.
yeah. No, I mean I agree with you. There could be I want to see a calculation, right? That matches both the Landau fan and the Hubbard bands or the Van Hoofs and the negative Seebeck coefficient. I think in the end this will only get resolved, as you correctly point out, by somebody getting the spectrum, these either Shahalilani or Dmitry Epitov with these microscopes, getting the spectrum and seeing if the spectrum has heavy light particles around.
So you have to see the heavy particles.
Well, I don't have a microscope, and they can't get, they got to, they having, I hear from the street that Shahalilani has, can get to 4 Kelvin, but not right now. So, we just need 1 order of magnitude and we'll be fine.
Yeah, cool.
So, Andrew, about multi-band ED calculation.
Yes.
The MOT2.
In twisted MOT2.
MOT2,
Yeah.
right. So the UW parameter, I want to check with you if you agree on
The which one?
The UW DFT parameter. That does not even give a QAH state filling factor 1. We found a polarized state that is topologically trivial.
Well, depends what interaction you take.
That is from either 5 or 10.
I agree. I mean, I agree with that,
It's already larger than experimental value.
Yeah, I agree. You have to take I agree with you. Basically, there's an issue about the epsilon you take. But that's an issue that exists also in pentalayers, for example. You cannot match the large gap, as you well know, I think.
I'm not talking about pendulator.
No, but that's an issue that if you want to match things with the interaction, it always comes out, the matching is not perfect.
With the Young-John's DFT parameter, it works.
Well, I don't know, well, it depends what you mean with Young. You have 2 papers or 3 papers, one with DFT parameters of Young-Jung and one with DFT parameters of Zalatel and Stigley, which are, the ones in Young-Jung's paper are different, but then the ones in Zalatel's paper with you also a co-author are the same as ours. So I'm not sure which one to take, right?
All right, so just any last pressing questions? I think this is for the next pre-March meeting conversation then, or for the break. Thank you very much. Andrei.
Oh, yeah. Sorry about that.
All right, so I read ready. Our next one will be by Simon. Kekule spirals in twisted graphene model. Multilayers.
Yeah. Hold on. Andrei, I'm blaming you for this.
Oh, maybe you guys can continue.
No, this is part of the,
Yeah.
it's good, good, good scientific conversations. Exactly. Thank you.
Okay, well, almost there. On the phone. Yeah, okay, it's
All right, please go ahead. Yeah.
all right, so sorry about that delay. So somewhere in the instructions, we were told to keep everything introductory. I entertained with Andrei starting by saying I assume everyone knows everything about twisted bilayers. I felt I wasn't giving enough introductory information in this talk. I was a little afraid it was going to be too advanced, but after Andrei's talk, maybe I'm not so worried. So if there's
Bringing the mic a little bit.
So this is work with, these are my collaborators. I want to particularly, the ones on the top row are the ones who did most of this work. Most of what I'm going to talk about is in this reference, so a little bits of the others. I want to particularly shout out Eve and Glenn, who are fantastic postdocs. They're both going to be looking for permanent jobs sometime soon, so please hire them. It's as far as the introduction to the field, the one most important thing we need to know about Moire physics is that you don't capitalize the word Moire unless it starts a sentence. It's not someone's name. It comes from the French fabric process, textile process, Moire, which comes from the word mohair, which is the wool of the Angora goat, which comes from the word mukayar, who's an Arabic word meaning chosen or the best, because the Angora goat is the best type of goat to make wool from. So anyway, so you can trace this all the way back, and you can say things like Moire materials are the best, and you can capitalize it here there because it starts a sentence. All right, so the important thing to realize about the physics of Moire materials is that when you twist the layers with respect to each other at a small angle, you develop a long length scale from the AA region to AA region where the lattices overlap each other exactly. And with the longer length scale in real space, you develop a very small reciprocal space, Moire mini Brillouin zone, and all the physics is going to be going on in that mini Brillouin zone. What happens is that all the bands get folded into the mini Brillouin zone, and they repel each other, and that's how you can get flat bands, very roughly, as pointed out by Mr. McDonald a long time ago. This is the same spectrum that Andrei showed a little while ago for magic angle graphene in the Bristol McDonald approximation. There are 8 central bands here. The nomenclature is that you count them from -4 when all the bands are empty to +4 when all the bands are filled. So 0 means that half of those bands are filled. The first experiments from this were done by the MIT group, and then there's a real explosion of activity. And the thing that caused this explosion of activity was these pictures, which excited people a lot because as a function of density and temperature, you see these superconducting domes. These are 2 different samples of slightly different twist angles. And you see these superconducting domes with metallic regions above and insulating regions, which they labeled MOT in between. And that reminded people of the high TC phase diagram. And immediately people started thinking, well, okay, if this is your Moire twisted graphene, you might think of these AA regions as being sites and have electrons hopping from site to site. And we know now that it's a little bit more complicated than that, at least, although Andrei is bringing it back to some extent. But there is a lot of similarity to that physics in that interaction creates the insulators. So this is some other data that Andrei also showed, that filling number of bands filled is listed across the top. And you see at certain integers, you get insulating states with high resistance. and some things that look like they're trying to get to high resistance, although they aren't there yet. And it's only due to the interaction that you see these insulators. You have very flat bands. If it weren't for the interaction, they would be extremely metallic. So the question that we want to ask is what is the nature of this correlated insulator? And I have the word usually sitting in there. And the reason I have the word usually is because not all experiments are the same as each other. It's actually a real credit to the experimentalists that in a very few short years, they managed to sort out why certain experiments are different from other experiments. Some particular features in the experiment that aren't controlled so well can differ from one experiment to another. In particular, how you align the sample with the substrate and the strain of the sample can differ. But in many, many of the samples, we claim that we're seeing the same correlated insulator, and that correlated insulator that we claim is being seen is known as a Kekule spiral. So let me try to explain what that is. Here's a graphene lattice over here, and I've colored every other bond red. So think of those bonds as being maybe a little tighter or maybe a little bit more electron density or something like that. At any rate, if you color every other bond like this, you've tripled the graphene unit cell. But there's more than one way to triple the graphene unit cell. For example, you could choose in some other bonds to make a little bit denser, make them blue over here. So there's more than one possible Kekule distortion. The idea of a Kekule spiral is that you have these Kekule distortions, and as you go from one AA region to another AA region, the type of Kekule distortion you get changes. So I'm going to describe the particular Kekule distortion you get as a vector, and the vector rotates as you go from one region to the next region to the next region to the next region, and the rotation of this vector is generally incommensurate with the underlying Moire lattice. Now, this is kind of an odd thing to have predicted. I'm going to try to explain to you why it's actually kind of natural to occur. But really impressively, this is a screenshot from a talk by the main authors, Knuckles and Ali Yazdani's group. So they, using STM, they saw exactly this. They measure the Kekule distortion in various AA regions as they go through the sample, and they plot it. Well, they plot it as colors, but they also give us a nice vector to describe what the type of Kekule distortion you're getting. That vector is rotating as you go through the system, and after you go through three lattice vectors of the Moire lattice, you get back to not exactly the same direction that you started with, but pretty close to the same direction.
And what color coding here means?
I'll explain. I may not explain it in detail, but it's basically, well, okay, I'll explain it at the end. I'll show the data a little bit more carefully, and then I won't explain it. So, okay, all right. So a good place to start the discussion of the twisted bilayer graphene is with the so-called chiral limit or flat band limit of the Strister-McDonald model. And there's more than one way to modify the band structure in order to get the bands to be flat. And that one way to do it is to take this hopping parameter from the Strister-McDonald model, which tells you the hopping in the AA region divided by the hopping in the AB region. It's usually taken to be around 0.8, and to tune it down to 0, and that makes the bands exactly flat. Now, we like flat bands a lot because that reminds us of Landau levels. And in fact, what you have in this limit is 4 bands with Chern number +1 and 4 bands with Chern number -1. So essentially, like a bunch of degenerate Landau levels all sitting right here in the middle of the picture. Now, I'm a quantum Hall guy, and I like Landau levels. So we use our intuition for what we know about Landau level physics. And when you have a bunch of degenerate Landau levels, for example, you could have a degeneracy of spin-up Landau levels and spin-down Landau levels. You could have degeneracy between, multi-layer quantum Hall systems. You get degeneracy of multi-valley systems. But whenever you have degeneracies of multi-component Landau levels, we expect to get flavor ferromagnetism of some sort. So when you fill an integer number of bands, you expect to get a simple Slater determinant ground state. So remember that you start your counting of bands from -4. So you fill some integer number of bands, 4 plus nu, out of the 8 central bands, and we expect to get some sort of generalized ferromagnet. The thing that makes it a little bit more interesting is that you can rotate within the Chern bands, rotate within these or rotate within these before you start filling the bands. In other words, you take a superposition. Okay, so I've labeled the bands here with spin, valley, and sublattice, and I can make a superposition of some of these combinations, superpose this with this, for example, before I start filling the bands. This is like saying I have a degenerate spin up and spin down, and instead of filling my Landau level with either spin up or spin down, I tilt into the X direction, and I fill in the X direction. I'm certainly allowed to fill the band in the X direction instead of the up direction or the Y direction. So I can sort of make a rotation before filling the band, and that's what makes this a little bit interesting. One comment is that whenever you superpose K and K prime valleys, that introduces a wave vector K minus K prime, and that triples the unit cell or makes a graphene, a Kekule distortion of the graphene, which is what we're going to see. All right, so this approach was all cooked up before I ever got involved in the problem, and it was done by a number of groups. They all sort of come up with very similar conclusions, and this is more or less what comes out. So you have to put back into the model some things that you left out. So interactions, you have to put in to decide which direction the ferromagnet, which direction of this pseudo spin is most favorable. You have to put in the interactions, you put in the single particle dispersion, and you select out what we call the strong coupling insulators. We call this strong coupling approach because you're starting with a completely flat band, so there's no kinetic energy at all. And that means the interaction is fundamentally a large perturbation. There's no small parameter. So following this approach, we get a phase diagram that looks kind of like this. At all these integers, you get various different ferromagnets that occur. One thing to notice is that whenever there's an odd number of bands filled, you always get quantum anomalous Hall, and that's easy to understand because you're filling either Chern number +1 bands or Chern number -1 bands, and if you fill an odd number of +1s and -1s, you're always left with a non-zero result.
So you include the non-chiral perturbation in these calculations or no?
So I didn't do these calculations.
Okay,
but it was discussed, yes, and
included in these calculations.
these are all considered, yeah.
And all of these states break time reversal, correct?
No, they don't.
IVC does not?
KIVC doesn't. There is a time reversal which is preserved in KIVC. So, yeah.
So if you have completely flat bands,
Yeah.
why K and K prime matter as points? Because you said there is a momentum K minus K prime.
That's right.
What selects particular momenta if it's completely flat band?
That's right. Right. Yeah. Okay. So, right. If the bands are completely flat and the interaction is chosen to be symmetric, then any direction in the space is okay. So you have to put in a couple of perturbations that you left out, the details of the interaction, any sort of the breaking of the, so that you're putting dispersion back in order to pick out a particular ferromagnet which is most favorable.
Okay.
Yeah. Yeah. Oh, maybe over there was first. Yeah.
Then probably strain would also pick something because strain would necessarily distort your band in a particular direction.
You could do that as well. Yeah. Andrei, did you?
But you do agree that there's a huge manifold of low lying.
Yeah, absolutely.
Very low lying.
Absolutely. There's a large, and that's going to be, yeah. Is there another one? Okay. Okay. At any rate, another thing that I'd like to point out is that in this approach, one thing that comes out at even fillings, rather generically or often, is intervalley coherent state. That's where you superpose K and K prime, but one with a particular Klammer's symmetry, a type of time reversal, which because you superpose K and K prime, you do have a tripling of the unit cell, but you can't see it in the densities. The density is completely flat. It only shows up in the currents. So that would be.
Say that breaks time reversal, but okay, there's some modified time reversal.
It's a modified time reversal. Yeah.
How about the IVC? The Kekule, the TIVC, or is it your IVC?
Okay, so there's several versions of TIVC that you can think about here, so in a later slide, I'll discuss that there's some that we can't distinguish between. That there's one that has one and another has another. But these, I believe, I can't even remember if this was supposed to be TIVC or not. This is not my work. This is
okay. Go on.
Go on. Yeah. So the thing that I liked about this approach is that it gives you a nice reason to understand why it is that the correlated insulators at integer filling are insulating, because it's basically just flavor ferromagnetism of a sort. You're filling up bands, and this is always what you get when you have multi-component quantum Hall. but it actually disagrees with experiments in a lot of fundamental ways. A couple that I'll point to is at filling -1, 0 and +1, it's often not an insulator, semi-metallic, although sometimes it is an insulator, but often it's not. And the other thing is that at filling 3, you often get a insulator with 0 churn number, which is not predicted by this approach either. If you align your sample carefully on the sample in a certain way, it will come out a quantum anomalous Hall state with a non-zero churn number, but generically, if you don't take pains to align it, it's churn number 0. Okay. So what we wanted to do is we wanted to go beyond the strong coupling approach and take into account some of these perturbations from the get-go, that we don't start with an exactly flat band. We want to put in the particle symmetry breaking terms, the potential from the substrate, and the one that actually turns out to be fairly important, as Andrei mentioned, is strain on the sample. Substrate potential is also important, but I want to mention strain because that one actually surprised me a lot. So Yang Fu and his group pointed out that heterostrain has a lot of rather dramatic effects on these. Heterostrain meaning different strains on the 2 layers, has a lot of dramatic effects on the band structure of these samples. You can measure the strain by observing the shape of these pictures that you see in STM. And when you measure it, it comes out to be a small number, 0.1 to 0.7%, maybe even smaller, not too much larger than that. Seems like that's a small number, but actually it's enough to really modify the band structure quite a bit. And you might say, well, that's surprising. It's such a small number, but there's some large energy scales that are hidden here. The bandwidth of the underlying graphene goes into the calculation of what the effect of the strain is, and then this total energy scale is very small to start with. So really tiny amounts of strain, 0.2% strain, really open up gaps in this spectrum. This work by Parker et al. Studied the gap that you predict at charge neutrality. And how it was affected by strain, and it was found that a little bit of strain really degrades the gap, and that was rather important for comparison to experiment because, yes.
What is this strain? Does this strain break the symmetries of the continuum model, or
it breaks some symmetry? So it breaks some symmetry, but leaves others intact. So it keeps the C2. It keeps the C2 symmetry.
But it breaks C3?
It breaks C3, yeah. Okay, so what did we do? What we did was nothing more complicated than Hartree-Fock, although it's a fairly complicated Hartree-Fock to do for various reasons that I won't go into. And let me sort of walk you through what the results are. Each of these pictures at the different integer fillings, we've plotted a diagram as a function of the substrate potential and the strain. The strain goes only, in each picture, goes only up to 0.3%, so it's a rather small amount. And the substrate potential goes up to 20 MeV. I think if you try to align the sample with the substrate, you get substrate potentials which are a little bit higher than this, maybe 30 or 40 MeV, but it's not, these are the kind of numbers you might get if you're not trying to align the sample with the substrate. And a couple of things to notice here, the places with white stripes are places where there's no gap. And that's nice because often in experiment at filling -1, 0 or +1, you don't get it, you don't see a gap, it's metallic or semi-metallic. The depth of the color, with yellow being the strongest and black being the weakest, is the amount of intervalley coherence or the strength of the Kekule distortion. So you see lots of things with Kekule distortions floating around in this picture. You see quantum anomalous Halls showing up sometimes. But the thing I want to emphasize is IKS, and it stands for incommensurate Kekule spiral, is really ubiquitous in this phase diagram. And it doesn't take a whole lot of strain to get, at 0 strain, you don't see it. But if with a little bit of strain, you do see it. So for example, down here, it's a few hundredths of a % of strain is enough to push you into the incommensurate Kekule spiral. I should also say that at some fillings, I think it was +3 they looked at, Mike Zalatel, after this work, he did DMRG, and he found that the transition to Kekule spiral is actually at even the lower strain than Hartree-Fock predicts. Okay, so let me just say a couple words about what this IKS is. It has a certain version of time reversal. It does superpose the K and K prime valleys. That means it has a Kekule distortion. It breaks translational symmetry, but it preserves a modified version of translational symmetry where you translate and then you rotate between the valleys in a certain way. And that's the rotation of this Kekule distortion vector that I mentioned. Good. So generally the idea is that we're going to be hybridizing one valley with the opposite valley at different wave vectors. Instead of superposing K with K, we want to superpose K minus Q with K plus Q over 2. So instead, what we're sort of used to, the idea is when we have two lambda levels or something like that, you take a K state in this valley and you superpose it with the same K state in the other valley, and you maybe tilt the pseudospin in some direction. But here what we're going to do is we're going to superpose this point in this valley with this shifted point in the opposite valley. Now, as a function of this shift Q, you can plot the energy in Hartree-Fock, and you discover that the most favorable energy is at some finite value of Q. It's sort of a soft minimum around that point. The actual position of the minimum depends on details. It depends on the direction of the strain, the amount of strain, the substrate potential, but it's typically around a third of a reciprocal lattice vector, so somewhere in the middle of the Brillouin zone. Yeah.
Oh, I just wanted to ask, I don't quite see how the incommensuration like plays with your translation and valley flip.
So let me go to the next slide, and so to explain why this is happening, because that might be enlightening. So the precise value of this Q is something that's determined energetically, and it's generally incommensurate. So let me try to explain why it is that we get this thing. So so I think this is a really, I mean, we have various different explanations for this, but I think this is the one that's clearest. So what we do is we first turn off intervalley coherence. So we prevent the two valleys from superposing with each other, and we just do Hartree-Fock and get some energy spectrum for the two valleys. So you get some energy in, for the band in this valley. It has some high energy regions, it has some low energy regions, and then by time reversal symmetry, the opposite valley has exactly the opposite picture over here. Now, it's favorable from interactions, as is often the case in quantum Hall, to make a superposition between the two valleys. And in much of the Brillouin zone, you make sort of an equal superposition of the two valleys. So you're sort of, if you want to think about one valley as being spin up and the other valley as being spin down, you're putting the vector in plane in most of the Brillouin zone. But in some points of the Brillouin zone, the energy is particularly expensive in one valley. So you want to take your pseudospin and tilt it away at that point, tilt it out of the plane when you get to that part of the Brillouin zone, so you don't have to pay this expensive price. And conversely, there are some points of this valley that are particularly favorable in energy, and you want to point your pseudospin into that valley when the energy is particularly low. Now, the idea of shifting by Q is that you want to align the low energy point in this valley with the high energy point in this valley, and the high energy point in this valley with the low energy point in this valley, so that most of the time you want to stay in plane, but at some point you have to pay you have to pay the price of not being in plane, and you can do so. You can both avoid this high energy region and pick up this low energy region by tilting your pseudospin at that place. If you didn't shift, then you'd have to tilt out of the plane twice as often, and you only get half as good. You'd only be able to pick up, half as much of this energy associated with dispersion of the bands. Okay, so we sort of played this game where we looked at the dispersions in the shape of the dispersions in the valleys for different values of strain, different values of substrate potential, and the dispersion changes around somewhat. And we tried to guess, what value of Q is going to come out of Hartree-Fock just by saying, well, how do we align the highest energy point here with the lowest energy point over here? And that usually gives you the number pretty accurately, actually. Okay, so what's important to realize is that this, the physics that's going on here is something that you couldn't get if you started by thinking about a completely flat band. Because the whole point here is that you're trying to tilt out of the plane because the band is not flat, and you need to shift the values with respect to each other in order to line up the high energy and the low energy part of the dispersions. So it's a case where the strong coupling approach is not going to be very effective. Okay, so this Hartree-Fock approach, it agrees with experiments in a lot of different ways. So we have the sort of semi-metallic states here. We get the spin-on polarized plus and minus 2. We have a gap state with Chern number 0 at plus and minus 3. Although if you put on enough substrate potential, you've got a quantum anomalous Hall state at nu equals plus 3. Also, the most important thing is that the IKS that we're predicting is happening at very, very low values of strain and well within experimental limits, and it's observed in the STM experiment. So let me explain, just take a couple minutes and explain how the experiment works. 5 minutes. I'm going to take 5 minutes.
That's 4.
And explain how the experiments work. So first thing they do is they take a picture of the sample with the STM. It's roughly they're measuring density. And then they can change the total electron density. And when you get to an integer filling, like nu equals minus 2, you can just see with your eyes that there's a, the pattern looks different. That's a Kekule distortion. It's a tripling of the unit cell. So if you want to see it very clearly, what you do is you Fourier transform this picture and you see the standard graphene Bragg peaks. But when you have this Kekule distortion, you see these auxiliary peaks associated with the tripling of the unit cell. And these circular peaks out here are actually just twice those points. So what we're going to do then is we're going to keep track of these Kekule peaks. Oh, the fact that you see the Kekule distortion means what you're seeing is not KIVC, because KIVC isn't supposed to have any density modulation. So then we do the same, they do the same experiment, we, meaning they, do the same experiment at different points in the sample. And at each point, you take, you take the Fourier transform of the picture, and you get these, these six Bragg peaks. The 6 Bragg peaks contain 3 complex numbers worth of information in them. This is coming to your question. And you can divide up the 6 complex numbers into representations of the rotation group, which is a convenient way to do it, and plot them here. And what they're plotting in these pictures are complex numbers as color and intensity. Okay, so we have 3 complex numbers as colors and intensity. And what you're seeing is that as you go from one AA peak to another AA peak to another AA peak, the color and intensity in each of these is changing, which is mean the shape of the Kekule distortion is changing from place to place. And you can actually see that. Oops. All right. Back. Okay, it doesn't want to go back, so I can't go back up. I don't know why. Back. All right, this is a one-way talk, apparently. So I was going to show you that you can actually see with your eyes as you go from one AA to next AA that the sort of the shape of the Kekule distortion changes. And here they plotted it as a vector. So they chose one of these. I think it was a bond they chose. They just plotted the vector instead of the color. It's rotating, but not quite commensurate with the lattice. This is a simulation by Mike Zalatel and his postdoc Tomo, and they don't get the actual Q vector exactly right, but other than that, it's pretty it's pretty much exactly like what they see up here. And this is what Ali says they see in all the typical samples at nu equals plus and minus 2. In a few samples with ultra low strain, they see something different, but not KIVC. Maybe well, the reason they know it's not KIVC is because they do see a Kekule distortion, and KIVC is not supposed to give a Kekule distortion. So that puzzled us. And then Erez, who's sitting over there, said, oh, it's because you didn't include phonons. And we then took into account coupling to phonons, which would then favor a density modulation. And then you can generate two versions of IVC, TIVC and IVC for this form and this form. And at the level of our approximation, those are actually degenerate still. Okay, so at any rate, if you have enough phonon coupling, that would agree then with the experiment that you see something that has Kekule modulation, but Kekule distortion, but doesn't spiral. And then in my last 2 minutes, I want to mention that a later experiment was done in twisted trilayer graphene. So this is symmetric twisted trilayer graphene, where the top layer and the bottom layer are aligned with each other, and the middle layer is twisted. Actually, the fact that you can do this is kind of amazing to me, but you can align the top with the bottom. And it's sort of at the level of Bistris or McDonald, the symmetric combination of the layers basically comes out looking exactly like twisted bilayer graphene, and the antisymmetric combination gives you one Dirac cone left over. So you get a band structure that looks like this with flat bands in the middle plus one Dirac cone. And then, how different is that going to be from the bilayer case? So Stefan Najperg's group went looking for an additional Q vector, an incommensurate Q vector, and it's a different technique to look for the Q vector, but indeed they found one, and they actually even traced it as a function of filling. And so we went ahead and did Hartree-Fock, and well, okay, it's a little bit more complicated, and I have to say that our data doesn't agree exactly with what they observe, but we do see Kekule spiral states in various large portions of the phase diagram. So at least qualitatively it seems to agree. So let me just maybe summarize there that the incommensurate Kekule spiral it's certainly there in typical samples, and there's a good reason for it to be there. It explains a lot of the experiments, but the million-dollar question is whether it's going to tell us anything about the interesting superconductivity. At this point, we're still not sure. Okay. And
when you explained why you have incommensurate state, you compare it with valley polarization. These are charge orders, if I can use this language. I presume in your Hartree-Fock, you also looked into spin orders.
Sure.
Are they competitors or they're out?
No, so that's certainly something you can consider. I mean, the Hartree-Fock is completely unrestricted, so it could get you spin order, but it didn't seem to be there. And
far away all the time.
The spin orders, I don't think they're spin order states that are particularly low energy. I mean, you can get spin polarization, in odd fillings, you can get spin polarization, but no, spin twisting or something like that. We didn't see. I don't think there's a good physical reason that it would be there.
Oh, but if it turns your coupling, this current pattern, you cause some speed.
But I mean, in graphene spin order coupling, I mean, the real spin is really super weak. So
just mentioned this was part of SU4, right? Spin incommensurate order is part of SU4. So it's a question why this component is never a competitor.
Yeah, I mean, I think the spin is sometimes it's mainly a spectator degree of freedom, because a spin orbit just isn't there. So it mainly just goes along for the ride. So.
Yeah, so I guess you talked about the integer fillings. Now, in the same data, there is allegedly some radical change of the IKS pattern.
Yeah, so
Andrei should comment.
I had in the previous version of the talk, I showed that also. So if you go away from integer fillings, they see something that looks vaguely similar away from integer filling, but the pattern is substantially different. And it was pointed out to me recently by Mike Zalatel that there's actually there's sort of a calibration issue that starts to worry you, when you could mistakenly see long wavelength, something that looks like a long wavelength spiral due to a calibration issue in the experiment. So So the fact that you see something that sort of rotates slowly might be something that's an experimental artifact. So I'm less confident of that away from the integer filling. So
what does the Hartree-Fock theory say?
so right. So we did Hartree-Fock away from integer filling, and we do find IKS states away from integer filling, but in a lot of cases, it's sort of still there at the level of Hartree-Fock. But there's a lot of reasons why you would expect to not trust Hartree-Fock as much when it's gapless.
Can I, well, sorry, one last question about this. So there's a plot in the experimental paper that says that the amplitude of IKS ordering drops precipitously when you dope to maybe 20% of what it costs in a small range of doping. So is that something that you?
So that's, so this is why I could be very concerned about whether they're actually seeing the spiraling at all, or whether that's fake. I mean, the technique from Stefan Nagy-Perg, however, shouldn't have that problem. And of course, it's a different experimental system. So the fact that they still see a wave vector means, at least in that system, there it might be more robust and of course integer for the tri-layer, integer is a little bit fuzzy because you're stuffing some of your electrons in the Dirac band as well. So
But in the Hartree-Fock, does the amplitude fall rapidly or not?
I don't think so, no.
Okay, so that's a difference. That should be.
More questions?
But do you trust the Hartree-Fock at 20% away from the, I mean, there's
No, I mean, it's, how much do you trust Hartree-Fock? When you have a gap.
integer fillings.
Yeah, at integer filling, exactly. When it's a gap state, you trust it, and so it's fine. When it's gapless, you start to worry, and it's you try it, you see what it tells you, and then you can start to worry about whether it's giving you something sensible.
Maybe more question for Andrei. I mean, does the Kondo model give you a way of understanding why the IKS is present at zero strain?
IKS is not present at zero strain.
I thought you just said phonons did that.
No.
AVC get to.
It gives you a Kekule distortion, but not the spiral.
Oh, okay.
Yeah.
Well,
you can.
okay. Is that
All of this
also
comes out
the
natural.
Yeah.
Sorry, can the
All
Kondo
of
model
it
do
is
that?
natural. Yeah, all of this can be understood naturally.
So this is the first time I've seen Andrei's story about
Right.
IKS,
Well, I
but
mean,
for what I could absorb in
Kekule
30 seconds.
distortion is also a property of graphene that cannot coupling. Just pure graphene.
Yeah. Is it one more? Yeah.
So will the dynamical screening, how will the dynamical screening change your phase diagram?
The dynamical screening? Do you mean from the do you mean from phonons or from
No,
the
from the
electrons?
expectations.
Yeah. So we could I mean, you could do so you're asking us, could we do a more fancy calculation and do something that's more sophisticated than Hartree-Fock, like some and we haven't done, so we don't know is the short answer. But we did look at things that might be likely to give you superconductivity as far as dynamical screening, because everyone's interested in why are we having such high temperature superconductivity, which is still, I think, an open question. And to be honest, we certainly don't have an answer for that. Everything we tried, whether we tried phonons, whether we tried, various forms of dynamical screening, FRG, so forth, we couldn't come up with a good justification for the very high TC of the that's observing these experiments.
Okay, sorry. Yeah, we have a couple more.
Well, I just mentioned there's a paper by Matthias Scheurer and myself, we haven't done any. I don't think there's any quantitative calculation TC, but there's a proposal how the Kekule distortion is related to the superconductivity.
Okay. I mean, I think the issue comes out with the numbers, that we can get superconductivity, but when you try to put in numbers, we couldn't get the numbers up high enough.
Okay.
No, but let's take a precise statement. You can get superconductivity with coulombs and phonons, right? I thought your paper says no.
No, it doesn't say that. It says that you can't get it, that you can get, I mean, at low temperature, you can get.
No, but how do you screen the huge Coulomb?
There's always a way, at low enough temperature, you can always get it. But the issue is that at temperature scale we need, you can't. Yeah.
All right, last one. Yep.
Yes, it's just a very simple question. So in the random strain, the symmetry of the system is low. So I wonder in this case, is it possible to understand incremental order from some sort of Lifshitz term in the number of free energy?
Not that I know of, not that I know of, but it might be, I mean, you might be able to come up with something like that. I mean, I guess you know, you can probably come up with some sort of Landau argument for all of this. I think we played with some of these things as well, but the question is it going to be, you know, is the energetics going to be favorable? You know, that there's a lot of energetic things going on, and you know, it may not tell you much to do that.
All right, let's see one more time.
Выглядит, что постоянно двигатель на квадрат. Ну, это не надо. Значит, должен быть один останется, там, не два. Ну, то есть, ну, просто вот такое, да, то есть, корреляция. У это уже. То есть просто Фурье трансформ это обычный колонн. Да, это начало. Примесь надо. Да, значит, до края, мне кажется, если вы считали двумерный коррелят, да, то это можно просто в двумерном корреляторе положить y равным нулю. И это вот это. То есть, вот эта фигня про интеграцию, это эффективный x коррелят. Так сразу как вы должны проинтегрировать функцию Z, да, которая, для которого D фиксирована.
I know this is right before, but all the way there. So far, it's possible. Checks.
Yes.
Вам придется проинтегрировать по примесам, чтобы усреднить по.
Состояние Андрея до края. То есть нету отдельности и расстояния. Да, есть сумма квадратов, одна переменная. Этого я здесь не вижу.
В этом смысле.
Да, то есть кажется просто, что какая-то есть редактация из того, что делается одна переменная идет туда и обратно. Сначала делали препод по многим переменным, а потом взяли обратно, переделали хуя икса. И это вот туда-обратно, мне кажется, замыливает простую вещь.
Может быть, но здесь Z в конце концов постоянный, да, интегрируется только по y. То есть они... Нет, ну спорить, нет, это не вопрос.
Как проектировался, мне кажется, что если по одной переменной один, а вместо него делается два интеграла по одной переменной, вот это не очень разумно. Но вот это все, что я говорю. И мне кажется, это сразу видно, мне кажется, что будет вот такая сумма квадратов. Да, потом уже будет проектировать. И вот на этом этапе, когда вот я избавлюсь от проще брать. Один разделить на сумму квадратов, да? Сейчас, или потенциально прямоугольный, или...
Нет, мне кажется, просто
корень из суммы квадратов. Очень хорошо. Я вот от него свои. Вот один разделить на из x squared plus y squared plus z squared. По e в степени equal x, а y зафиксирован. Видишь, что y один интеграл по x. Помните, y squared plus z squared. Ответ будет если к сумму квадратов. Да, ответ простой. Разрез один интеграл.
Пожалуйста, но вы за это заплатите, когда вы захотите интегрировать
Кто мне будет заплатить?
Ну, окей, да, это есть интеграл. Каждый есть свой брат.
I'm not really sure much. I know that
Написать как интеграл.
as two of his PhD students at the moment for an extended day. And so once I know a lot of people are
Okay. Yeah, no, I have no quarrel. I don't even have a quarrel.
There's discussions.
And we would like to understand. It's just kind of funny that they invite
Enable you to explain. I got that in my own something.
Oh, that's fine.
So you will call point.
So you will go there. I doubt that he will go there, but I will let you know.
So it's trying to ask. Get away with what?
Yes, and last night.
So basically, some was. I want to look at it. As far as I can, I'm not opposed. I think I was on the spot, I will propose. Maybe it's not going to be. positive it's purely phenomenologically, I mean, post.
Mostly for on the light versus heavy.
Why would it not be? Sorry, I send it, but I still send you our papers.
What we discussed. Yes, I mean, the talk is amazing. I mean, like, I sent out some slides and he selected some of the slides because this.
I've heard it so, there's and nobody has given me an answer. Talked a lot. We reached an agreement, you know, that first one is and we said, okay, let's see whether there's ways to and the initial hope thermal power was that thermal power would actually the heavy qualification, I should see. There's heavy things coexisting with light things. You know, the heavy things will dominate. Because we don't know how to measure people fast. So I was hoping that maybe thermal power can be a proxy for
Thermal power,
but it has thermal power is complicated.
thermal power is complicated. I mean, we're not even talking about exploration. We open that Pandora box.
Yeah.
But in a simplified manner, it actually a very mass pretty much within one single line.
Yeah, no, I'm saying, but
In that case.
it often works as a proxy, but
Yeah.
it's not guaranteed. it works as a
Exactly,
proxy.
exactly.
So if you had seen a C-rate coefficient, linear T, but at the slope,
I can believe.
very, very high.
Maybe.
-2 plus something.
Yeah.
That's not steep.
Yeah, it's consistent, I guess.
Yeah, so I think there's a problem. Maybe good.
And this is remains.
All the experimentalists are quoting, every time I talk to an experimentalist, they say, oh, this heavy fermion, this, the carriers are heavy when you go towards neutrality. You have a system, what's the evidence? And nobody has it. Say, oh, I heard Andrei say, or I heard Oscar say, or I heard someone else say.
Larger density of states in some particular point at least. The number of
You're also like
all these elements
sketchy toward the flat work and communicate.
Yeah.
Carriers worth it.
then you can try
No,
to
it's
see
20 years
that
back,
there
it was
exists for the flat state. What we did was very gradually get out of the place because at that time we said, okay, Hagenbach gave us interactions and you will get up to an interaction. With all the numbers, we didn't play the game of where quantity. At that time, we didn't find, not moving forward in 0 for the not favorable. But
That's what other people do. But even before that.
What are the what can
Other people
Yeah.
know, but.
So actually,
But
is.
may actually not be that.
um,
So I'm afraid that this heavy polyparticle may be one of
The
those
data,
things which.
if you look more carefully at second,
It seems like this consensus building that they're there.
So they
zero
look at
evidence.
what seems to be, it's always hard to identify what is each there. But.
So conceivable that something, I mean, first order transition is the most obvious.
So,
But
they find the influence for water at the. No, I mean, there are even fancier, like,
Yeah.
BMFE. And they see it again, and figure out a distance from the.
one different order.
It could be a different order, but it seems to sort of lie on the same line. And the fact that you probably have to ask experimentalists, That's the
But
take of
they definitely
a
tend
thing,
to
I
have
guess.
points.
That's the state of things.
And so it could be that
Sure.
it's disappearing between two different order arrives. When you kind of band to sort of have.
It's good to be clear.
If you're inside the metal sense, they use what's actually.
Well, in the
I
triangle,
know
you still
those two
use
things are being
to some extent.
I see, I see.
by the community as a whole. No, not just.
So there's other things.
Because the approach this one is metallic.
A lot of other things, there's a lot of other things. I think. I agree that not all.
Are you guys
All we
involved in
know
those,
is two papers.
No,
And there's additional data.
two of you know.
No.
It is kind of interesting.
So you have to discuss directly. I
see
don't have
why the two phases.
Yeah, that's fine. I will not find on it because I'm leaving this after my call. But then maybe I'll just. No.
Yeah.
Close to cancer.
Yeah.
There's a bunch of fun.
Yeah. There's so much in Japan. Yeah.
Yeah, I know, but. I just like to one day, I think that.
Yeah.
Yeah, we don't actually disagree as much as he wants to say we disagree. That's. I understand the reason for that, but. It's what it is, but.
Technically speaking, it's first order thing is not
What's less option, but still.
not that incorrect, but you really want to argue. I believe that Andrew's hybrid model is correct. It's no harmonized. That creates the F value of the Fermion again. Still like a very nice thing. Yeah.
General, even if you love it. Construction shows.
You're talking about TVG or.
Yeah.
Some of it's arguing, right?
Yeah, exactly. It's just like about semantics.
Key draw.
It's also like the first thing, like whether we agree like the model is correct or we want to some other model stuff.
Is there a simple?
Agree the model is correct.
Move first.
I didn't see like okay, it's not fair to say like in our calculation there is anything of first order. Yeah, it's probably not a fair argument.
I mean, there is.
But it's not just like you dope a little bit and just suddenly jump on some others.
Yeah, exactly.
In this case, even just.
Stabilize this for a bit. And
That
that's
structure that.
Lots of parts.
Yeah, but I still like that. He don't be doing this. I mean, pretty good or what? I kind of like don't understand which part he disagree with Andrew. I mean, I can understand he's. First
Well,
of
it's
all,
untwisted.
Understands maybe parts.
It's more by the system.
Large.
okay.
It's more definitely for this. And again, you can say, you do it materials.
Yeah.
So there is a chance, yeah, exactly. More than
It's dimension.
because you get when you deal with Sally or C.
Correlated. It's
Yeah.
Everybody must have large left.
There's more for more than one for the start.
Yeah.
You can have different more than.
Yeah. There's a lot to be sorted out.
Okay. So I heard like he said he agreed there the lifetime. He's using like their.
Same time.
Yes, one minus x or like minus one plus x. Zero plus.
Yeah, that I understand, but you also talking like the integer field, like these people are trying the integer field would be like the how you want to have it now.
Yeah, of course.
Okay, thanks again.
So, maybe,
Then the C-base is.
Yeah, is there coffee out there?
yes.
Okay, let me go do that.
Actually, some reason I asked about the dynamic screening is because I did some calculations.
That is something I've seen for a while. So I never,
Oh, okay.
I never find a way to really like.
Yeah, okay.
study it.
I can.
Oh, okay.
Like basically what he's saying is like. At least, well, I mean, in principle, here's the thing, you do have this.
Yeah, exactly. We didn't try, that's pretty long.
Well, why don't you connect and you connect with the
Boss. And to the boss? The big one, by the name R.
Oh, the five.
Yeah, he is the chair, he is the chair.
Oh, he's the chair.
Yeah, I'm ready to do this.
So this not connected.
Really?
Yeah.
We need to, but he
I need to do something.
yes.
All right.
There are two people who know, Natasha knows, and, but they can see her. No. And Rafael is supposed to know, let me.
That, you can try to connect. Mine is there.
Get a cup of water.
Yeah, sure, but,
What's the
yeah, I
question?
don't-
Yeah, do you know how?
Oh, yeah.
Yeah.
Which one did you connect? A USB-C?
Yes.
Very good, at least one guy. Good, excellent. So now I can just connect and.
I'll let you know when I find it. I think so. The hot thing I'm looking forward to the.
Unfortunately, you won't be able to.
Nothing at the margin.
Serial number is yours. If anyone lost $2, seriously, on the coffee table, that's there.
I can tell you what color it is.
You think?
Maybe it's a two. It was a two.
Senthil?
Yeah.
Did you lose $2?
Sure.
Serial number.
I'm not sure it wasn't clear in the piece that it's.
I don't think it's real.
Yeah, our first speaker will be Dave Goldhaber-Gordon. Disordered prospects for control of other walls or instruction.
All right, good, all right, yes, so, yeah.
That's some they did kill this, which you don't do, but at least people see.
Okay, so I really enjoyed this, the stimulating workshop, and, as, as Mike Manfra mentioned yesterday, you know, he was the first experimentalist to speak, and that situation hasn't changed very much. So I'm going to, I think that the other talks this morning have been provided a lot of motivation for what's exciting that's going on in 2D Moire systems, but I'd like to give a couple of other vignettes about that, but really just touch on them and mostly use all of this as motivation for where should we be going from here, and where is the field going. So just to remind you, since we've seen lots of Hamiltonians and also lots of beautiful SDM images, and you know, how is the sausage actually made? You know, for starting 20 years ago, the Manchester group took bulk crystals of graphite, used Scotch tape, Scotch magic tape, pressed the tape on the graphite, folded it over, and pressed against the substrate. And lo and behold, when you search on the substrate, I think in a certain sense, the key insight that led to the Nobel Prize was realizing, either by planning or by serendipity, that they could see single atomic monolayers on a properly chosen substrate in just an ordinary nice optical microscope. So that was 20 years ago. How has it changed now? Well, not a lot in many ways. So of course, there's been a lot of development. So for example, there have been a lot of developments, especially at Columbia University, that have propagated through the field on how to do stacking of multiple layers. I'm not going to go through the details, but this is encapsulation within boron nitride, another very perfectly flat material, but in this case, an insulator that does a good job of protecting this a material that's all surface from the outside world, which is necessary if we want to try to make it clean. And it's really astonishing that in air, one can pick up these multiple layers and end up with something that if you look at a TEM image from the side, a transmission electron microscope image, that you can barely, we have to mark the graphene as a layer within this stack of boron nitride. Otherwise, you wouldn't necessarily even know that this is graphene. It looks, and we can't say it's epitaxial, it's not, but it looks as if these were grown in a fancy system like Mike's, but they were actually made by just peeling these with Scotch tape and then with a squishy, sticky stamp, picking these up one at a time in air. And so, so how?
David?
Yes.
You might acknowledge that Scotch tape itself was invented a few months.
That's correct. 3M. Yes. So
to start the story.
Absolutely. That's a very good point. So how is this actually done? This is stacking setup from my lab that is the second one that we've built, and I'll show you a more recent one. This one was built with some refinements from my then student Aaron Sharp visiting Pablo Herrero's lab right after the explosive announcement of superconductivity and twisted bilayer graphene. And so you can see that this has a lot of knobs that we can use to move on a substrate and something that holds the stamp. And then there are two control knobs that are motorized and more precise, one to bring these together with nanometer precision, and the other to rotate one with respect to the other for making a controlled twist. And so then this is what the stamp looks like. It's, as I said, squishy and sticky and goes on a glass slide. All right, so now let's do the twist. There was a development made by Pablo Herrero's group and independently by Emmanuel Tutik's group at UT Austin. And this is a refinement of the stacking in which one can arrange for a controlled twist between two layers. And the trick there is that you start out with one layer of graphene and you pick up half of it, then go over the other half and rotate by a known angle, pick up the other half. So as I mentioned, we have a rotation stage that is good to, it's good to better than 1,000th of a degree. So, so although we don't know the global angle of these two, it seems like, all right, we should be able to do a great job of controlling the relative angle of the two, which turns out to be an overstatement. So here's just a cartoon of a layer of graphene and then putting another layer of graphene, and you see the Moire structure made by the fact that the two of them go in and out of registry due to their small twist angle. So what are these twisted stacks good for? You've heard some remarkable physics this morning that comes in part from twisted structures, in part from non-twisted ones. But I would say here's a not very controversial list of what's exciting about them. We have this new tuning parameter, twist, that allows us to adjust various things, including the relative importance of interactions and hopping, and also allows us to adjust band topology. For all these 2D samples, the Moires and just non-twisted systems or non-Moire systems, we can adjust the carrier density and the electric field normal to the plane by using gate electrodes. And for the Moire structures, the tuning with a gate allows us to go over entire bands. And so that's powerful. You've seen, when you have a band that can host up to 4 electrons on a Moire site, that one can actually go to 1, 2, 3, 4 electrons for a Moire site. And that's because with the Moires, these are spaced laterally by enough And if you tried to do this in a single atomic layer of copper, you'd have 5 times 10 to the 14 electrons per square centimeter. And before you could get enough electric field to substantially change that population, you would break down any dielectric that's available. So by making these sparser, we're able to go over entire bands. It seems like there's a good prospect of having low disorder because graphite can be, in some cases, very clean. Graphene from good sources of graphite treated well can have essentially no atomic scale disorder. That is, in STM, people can search over a square micron and find no defects. So it's really, from the atomic point of view, very clean. But as we'll see, new forms of disorder creep in. In fact, you sort of heard about that in the morning about strain is important. It varies over a sample. These systems are exciting because the chemistry of the system is much simpler than, say, in the cuprates. We have just carbon notionally, and so using the Bistritz or McDonald approach, it's possible to really very nicely connect with many refinements made by the community since then to connect electronic structure to the atomic structure in a really detailed way. I'll show you a bit about that as we go forward. And you can stack anything on anything that's certainly any 2 layers that are exfoliatable, but you can also put these on other substrates. And all right, many amazing things have been seen in this context. So I'm going to tell 2 vignettes. I'll gesture at one and in slightly more length tell you about the other. So first of all, you've seen this picture, I think, many times, including this morning, the discovery of superconductivity in twisted bilayer graphene by Pablo Herrero Herrera's group. Many groups around the world got really excited at that time. I mentioned that my then student Aaron Sharp flew to Pablo's group to get a little training on how to make these twisted structures well, and he actually flew there in a blizzard and was nonetheless hosted in the lab, which you'll appreciate in Minnesota, and came back, built the stacking setup that I showed you, and my group's first attempt to reproduce superconductivity, Aaron saw it wasn't superconducting, and instead he looked at the sample quite carefully and ended up seeing something that was really striking. And we've heard a little bit about this morning. We'll hear more, I think, from Senthil on development since then in this area. The Hall effect at a particular filling at 3 electrons per Moire had this striking behavior that when we sweep magnetic field over a very small range around 0, that the Hall effect is big. It's on the order of 10 kiloohms, and then it's pretty abruptly, sometimes in a number of steps, drops and switches to the opposite polarity. And then it remembers this, and when we sweep back from the other field direction, we get a hysteresis loop. And so this was really, it told us, all right, this is probably magnetic, but that was, to us at the time, probably not to all theorists, but it was quite surprising to us that it was magnetic because this is carbon after all. It's not cobalt, nickel, iron, but beyond that, what should have been equally striking was the fact that we saw a significant Hall effect. People are probably familiar with the anomalous Hall effect, that if you have magnetization, that can induce a Hall effect even in absence of magnetic field. But first of all, that's usually milliohms or ohms. And secondly, it requires spin orbit coupling normally, because if you polarize spins and then you drive a current, these, say, spin up electrons are not selectively going to go to the left side of the sample. They're going to go just as much to the left and the right unless you have spin orbit coupling. So this theorists quickly recognized that this was, and helped us see that this was an orbital magnet. That is the first magnet that I'm aware of that was seen near zero magnetic field, where the magnetization came from circulating current loops, not from spin. And secondly, the size of this anomalous Hall signal is suggestive. It's around 10 kiloohms. It's on the order of the quantum of resistance that led us to speculate that this was a Chern insulator, and there was other evidence for that, but certainly this was not close to quantized. So I'll get into where things went from there, but why was this sample different from all other samples? Well, I wouldn't say I was tempted by that language because of Passover, but really it wasn't all other samples. There weren't that many at that time. But Aaron looked back at photos he had taken while making the sample, and he saw that the edge of a piece of one of the pieces of graphene was nearly perfectly aligned with the edge of one of the boron nitride layers. That was an accident. So Steve, I think, said you can arrange for a particular twist angle. Well, we didn't arrange for that, but it happened. And so this seemed suggested that was probably in some way related. And in fact, thinking back, both Pablo's group and mine had seen 5 years earlier that even though normally we tend to think of boron nitride as just this inert insulator, in fact, it has almost the same lattice constant as graphene. And it was known by this time that in monolayer graphene, one could actually open a gap at the charge neutrality point by breaking C2 rotational symmetry by stacking on boron nitride, particularly with small twist angle between graphene and boron nitride. So this might make it easier to polarize a system. Opening a gap at the charge neutrality point might make it easier to polarize this fourfold degenerate band.
What are the dark spots?
Yes, that's the dark side. So so these are bubbles. So it's a miracle that in air one can put these layers on each other and get them into atomic registry, which is what's necessary. If you want to have a Moire band structure, they have to actually be intimately in contact. And yet we know everything in air is covered by a thin film of water and adsorbed air and tiny hydrocarbons. And the magic of this stamp procedure developed at Columbia is that when you pick up a layer, you roll the stamp on and you squeeze out the adsorbates. But they don't go away, they just move around. And so then you try to find a region that's far from them. So you can see this is a 10 micron scale. And if we're going to end up studying a few micron region here, we can get pretty far from the bubbles, but this is a harbinger of problems to come. So we, Aaron and I went around talking about this work in advertising. It seems that you need to align with boron nitride to near magic angle graphene. And Andrei Young's group looked in their back catalog of samples and found one that met this set of requirements. And indeed, they found near quantization in the anomalous Hall effect. So they not only reproduced what we had seen, but they had this very beautiful result that you can really see this is a Chern insulator. Now, since then, there have been other orbital magnet systems. An example that I was involved in is ABC trilayer graphene aligned with boron nitride. Turns out that's a rare system where you can get either a Chern insulator or a superconductor, depending on how you push the electric fields around. This is work with Feng Wang's group and others. And that's just one example. There's a whole laundry list, and we're going to hear about even some of the exciting recent fractional work. We heard a little bit from Andrei, and we'll hear more later today. But what about twisted bilayer graphene? It's been 4 years or a little more than 4 years. And there have been hints of orbital magnetism near zero fields in twisted bilayer graphene. Efitov's group and Amiria Kobe's group have seen what look like churn insulators at small finite field that extrapolate in a way that it looks like they're just not quite stabilized at zero. In Amir's case, that's mostly with local compressibility measurements. Ali Yazdani's group and Eva Andrei's group have seen evidence of the sort of swirly wave functions that that would be associated with orbital magnetism. But all this time later, we've the original 2 samples have been measured quite intensively, including by a range of techniques, and we've learned a lot. And yet, they are the only 2 samples of their kind in the world, to my knowledge. And so that's frustrating. And it's not that people haven't tried. My group has tried. Andrea's group hasn't very much because he decided that twist is the devil, and you know, I think it's good to have strong views on that, and we can get back to that. But what's going on? So here's again, I showed you this cartoon of graphene, another layer of graphene. What's going on with the boron nitride? After all, that had only a small twist angle. And even back when we originally saw this, I mocked up what was the what did the boron nitride orientation look like. It turns out we could conclude that from transport. And here's what the boron nitride looks like sitting on it. And you can see that the boron nitride graphene moire lays almost perfectly on top of lies almost perfectly on top of the graphene moire. And that was, you know, at the time I said, well, maybe all that matters is that we have some small twist angle near zero, and that breaks C2 symmetry, which favors opening a gap and polarization. Or maybe it actually matters that that these moires are locked together. And if so, then there are 2 sub-possibilities. One is that nature is kind, and it helps that lock-in. And so if you're close, it'll tend to favor that. And that's, we heard a little bit about the twisted trilayer graphene, where you have one layer, a twist, and then come back to the first angle. And I think, is it Steve, you said that, you know, it's amazing that that can work. It is amazing, first of all, that people can just get this technology to work, but they're going to be a bit off, the first layer and the third layer. And yet in the region of overlap, it turns out both Philip Kim's group and Pablo's group find that it's closer than you'd expect, that it likes to adjust. So it's not crazy to think that but a final possibility is that we just got exceptionally lucky. And I at the time refused to believe that, because, you know, this is our first sample, and already we see it. But in the meantime, I think I've been forced to grapple with that possibility. So what may be going on? I'm showing something based on a figure from a paper from Alan McDonald, but there have been other independent works by Senthil, by Paco Ganea, and others on this. And so here I'm showing the graphene angle, and the familiar magic angle is around 1.1 degrees. And so these blue spots are intended to say, you know, something good happens there, which is that you could get this churn insulator stabilized at filling factor 3. So you need to be near magic angle for the graphene, but that's not enough. You can't be at 0 twist angle with the boron nitride. That would not form a commensurate moire. And you can see that because if you have 2 systems with different lattice constants, the moire will run along the irrational lattice directions. Whereas if you have 2 systems with the same lattice constant but a twist, the moire runs at 90 degrees to that along the theta direction, or 30 degrees from that if you prefer. And so so at 0 degrees, you can't get simple commensurability, but it turns out that at about 0.6 degrees for boron nitride and 1.1 degrees for the graphene twist, you can. So now it starts to get pretty tough. You need to match two twist angles, not just one. And one of those twist angles, you can't use the trick that was developed to get a certain twist angle. You can't start with one piece, one crystal, and make a twist of one layer with respect to the other, because this is between two different materials.
Sorry,
Yes.
is this a theoretical plot?
This is a theoretical plot.
And what is the criterion to cover this region?
So there's strictly speaking, one point where there's perfect commensurability of these two. And as far as I can tell, I'm open to someone correcting me on this, but as far as I can tell, the fact that the match of the two moires happens at almost the magic angle is an accident, a cosmic accident. Because if the boron nitride lattice constant were 3% different instead of 2% different, it would happen at a different angle. But it seems that, at least in this case, it does happen at that angle. So what's the blue blob? That's a little bit impressionistic, but it's mostly saying when you go away from that, you start to get churn insulators locally that are in opposite churn numbers. And this blue blob is basically where you have percolation of one churn number over the whole sample. I mean, not that the whole sample is one churn number, but that you have a connected percolating region. So, so these points that I added here, this is representing what we know about our twist angle in our sample, our original sample. This is from Andrea Young's sample. Here they don't know, it wasn't clear which way the boron nitride is twisted, but you can see that, right, they saw churn insulator and they were closer to this perfect orientation. And even there, their sample turned out to be quite inhomogeneous and I think lucky. So, so I hope I've illustrated a problem, but also an opportunity that once we go beyond one layer of a material, every sample is different. If you have one layer of graphene and you keep it very clean, then you can do a pretty good job of consistently seeing very similar behavior. But beyond that, we have twist. We knew that was a tuning knob. I'm going to show you that strain is important. We've heard that from Steve also. And these parameters, we can be extremely sensitive to them. And it turns out we can't control them very well, even twist. So the approaches to trying to deal with this that are happening in the community are, first of all, the dominant method, which is to make many samples and focus on what's interesting. So literally someone who I respect very much in the field said to me, commenting on the work I've been doing for the last several years, trying to be more consistent about stacking, saying, why don't you just do like us? We make 100 samples, find the hero sample, measure it for 6 months, and write your great papers on it. And that group does excellent work, and that's emblematic of what's happening in the field. So it's been a highly successful strategy. I think that it's hitting its limits.
One question: what's the time commitment to make one sample if we can not grow?
And so there's coming up a learning curve, but I would say someone who's really adept at this to do the exfoliation and stacking could be a matter of a few hours to a day, but then you go into the clean room and you do nanofabrication, multiple steps. So it's I would say basically a week to make a sample, and then you need to cool it down to low temperature because if you can't evaluate how it is at room temperature. So so another approach is to have something that's inhomogeneous but look locally. And so we heard Steve telling you about the beautiful STM work, and there you look here and you have Kekule in one direction. You look there, it's Kekule in another direction. Somewhere else, the strain is lower. You don't see Kekule, so you have a whole universe in the one sample, and you can be happy. And that's also very fruitful. You can intentionally create inhomogeneity. So this is a cartoon from Corey Dean's work on bending a ribbon to get a gradient of twist angle and a gradient of strain. in this sample. So you can, if you look in a small enough region, it can be pretty uniform. You can tune in situ. So this is showing a cartoon of Shachal Ilani's twist microscope, which was mentioned. Or what I'm going to talk about is you can try to improve stacking, or I'm going to wave at improving stacking. And the reason that I like this relative to the others is that if you come up with a theory that says if you change this parameter, then you'll see this effect, then it's a little bit, it's not ideal to just look locally the disordered landscape you have. You can do a bit with creating a gradient, but still it's then you're left with very small regions. The tuning in situ is fantastic, but only if you have one tuning parameter, twist angle. If you have to do something like strain or multi-layers, you're stuck. So I think that these are all should be pursued, but I favor this one. So since I'm running out of time, I'm going to gesture at this this second vignette, which is just, and what I want you to take away from this is that you can, first of all, you can try to stack it at magic angle and get far off from magic angle. This is almost 1.4 degrees. Secondly, that something that we didn't suspect would be important can make a tremendous effect on electronic properties. This turns out to be strain in this case. So this looks pretty innocuous. Here's charge neutrality point. Here's full filling of a band. And there are no strong features at integer filling of the Moire. That's as you'd expect, because this is not such a flat band at this twist angle. But then when we turn on a magnetic field, you can see that the longitudinal resistivity goes up over a broad region on both the electron side and the hole side. And this is a log scale. So we get as much as 300 times magnetoresistance. And so that's not unprecedented, but such strong magnetoresistance has normally been seen in semi-metals, and you need to have near compensation. You can go back to Ashcroft and Merman for that. Here, over a broad range of densities, we see this strong magnetoresistance. It was really pretty shocking to us. We see changes in the quantum oscillations compared to what we'd expect, a doubling of some of them. You can see the magnetoresistance is near quadratic here. And then if we combine the gate voltage with the magnetic field, here you see a Landau fan, and it's extremely rich and complex, but we can assign certain Landau levels, and there are some really unusual things that happen, like the splitting of these Landau levels as they come into this magnetoresistance region. When the Landau levels cross, they have a very ornate structure. Half the Landau levels terminate when they come to the magnetoresistance region. And Joe Finney, my student, and I, for a year, showed these data to people, and they said, they're beautiful. We've never seen anything like it. We have no idea what's going on. So Joe got frustrated, and fortunately, he had spent 2 years at Google in between undergrad and PhD, and so he wasn't afraid of doing some numerics, and he decided, just as a toy problem, to model the Hofstadter butterfly. He knew it was not the right model there. He then tried to add terms. He added anisotropy, so different hopping in two directions. And I only later realized he accidentally added unit cell doubling because his code had a bug in it so that he could hop 2 cells over. And when putting these in and looking at the density of states in the system, you can see some remarkable resemblance to the things I was showing before. And I will skip the details, but here's an example of data and a basically 2-parameter attempt to match it with the model, which again is the wrong model. Here now it's on a triangular lattice, but it's not the Moire. And it's remarkable how well it matches. And it's been a saga of years that's been very much helped by working with Oscar Vafek and Xiaoyu Wang, who've done really remarkable work. But I think that we now understand that that this is caused by strain and about 0.2% uniaxial heterostrain. But that was an accident. We were able to get back that sort of behavior by making more samples and intentionally trying to stretch one of the layers. But we lack control of the key structural parameters. The twist is typically off by about 1/10 of a degree from what we want. There's inhomogeneity, and no one's really controlling strain in these structures. So we've together with a colleague, Andy Mannix, at Stanford in material science, who's a pioneer in stacking and vacuum, we built a stacking system to try to get better control. And what we realized is, we made tens of samples and we said, all right, how can we tell, are we doing well? And just as in MBE, you need to have some in situ process monitoring. Here, we need a new set of eyes for being able to see, are we doing well? And so I'm going to take 1 minute and then I'll stop. There are a bunch of things in the literature using variants of atomic force microscopy to try to map moires. Of course, there's beautiful scanning tunneling microscopy, but that requires doing a lot of fabrication, cooling a sample down to low temperature. We wanted something that we could do at room temperature. And there was encouraging work from Columbia that suggested we could use a technique called piezo force microscopy to try to do this. But we and others tried doing it, and we found that it was very intermittent whether it worked. Maybe 10% of the time it worked. So here's a sample on a stamp. So you're looking at a polymer stamp, and then it's been flipped over. There's a boron nitride piece that's tens of nanometers thick, a piece of monolayer graphene here, and we'll look at those two. So first of all, using this technique that I'll just briefly introduce, we can look at the boron nitride region, and remarkably, we see the atomic lattice. And that was a real surprise. This is not an atomically sharp tip. We used sharp tips, 5 nanometer radius of curvature, but we certainly didn't expect at room temperature in air in a shared facility tool to be able to see the atomic lattice. If we look at monolayer graphene that's sitting on boron nitride, there's a moire. And if we zoom in, we can see the moire and atomic lattice structure. And so I guess I won't describe the technique much unless, but people can ask me afterwards. But this is a technique which we think is measuring in some form friction, and we can optimize the parameters and get maps of moires that look like this. And we can take, a pretty big region, half a micron, zoom in, zoom in, zoom in further, and see more and more detailed structure. And we can also look at bigger regions, and we can see inhomogeneities in twist and strain. And so for this part, since I'm out of time, I'm just going to show the problem and not how we're trying to solve it. But here's a beautiful moire image. And so you can take the Fourier transform of it, find what the periods are, and try to extract the structural information. And we do that. But and you can see that the wavelengths are, let's say, 15 nanometers, a little bit above, a little bit below 15 nanometers in the different directions, suggests that there's a little bit of uniaxial heterostrain. But this is the image as we take it. And in fact, the image may be distorted by the fact that the tip doesn't go where we want it to, or there's drift in the sample. And so we need to account for those, and those can make a really big difference. So if you just want a beautiful image and you want to say the moire is uniform, that's something that is now straightforward. And anyone who wants to do it, I know you're mostly theorists, but we tried to make it in our paper very accessible, and people can contact us and get additional help. But if you want to get quantitative information, it's a substantial additional effort. And I think we've now gotten to the point that I think we can assign twist angle to about 1 to 200ths of a degree, and strain to let's say better than 1/10%, maybe a bit better than that. So we're still working on it, but I think that this new set of eyes is a key big development, and I will close with that. I'll just say that the people who did this, Joe Finney led the strain work, Aaron Sharp led the work on the orbital magnet, and Mihir Pendarkar and Stephen Tran did the work on this new microscopy technique and an analysis of it. And thanks very much.
Yes, go ahead. Bernard, I say that I can see how eventually you'd be able to control twists to whatever 100th of a degree, but if it's so explicitly sensitive to strain, how are you going to control it?
So that's a big question. I don't have a perfect answer, but what I think I can say is that as Mike said, strain is very important, and it's heterostrain, that is strain of one layer relative to the other, which distorts the appearance. It's magnified by the Moire and has a big effect on electronic structure. And so if we just grab the whole thing and we stretch it, that doesn't help. So what one approach that I'm trying is stretching one layer before we pick it up, stretching the substrate, and then picking it up while it's strained. And so I think that's promising, but we're trying a couple of other approaches to it.
So quick question. So you showed this outsider spectrum and magneto resistance.
Yes.
So where you see large magneto resistance, is that how is it related to the Hall coefficient and no T?
Very good question, and I think it's a longer story, but the large magneto resistance is centered around half filling of the electron or hole band, and so that's around where you'd expect the Van Hoff singularity. And so, in fact, at the time, we were just sure that it was there. It turns out that we were wrong. There are. I'll just go to the relevant slide and point to the places where the Van Hoff singularities actually are, but yeah, okay. So we were pretty sure that the Van Hoff singularities were here and here, and that had something to do with what was going on. But of course, in the presence of strain, there's a splitting of the Van Hoff singularities, and there are actually three of them. And it turns out one of them's here, one of them's there, and in between them we have 1D-like Fermi surfaces. That's something that Xiaoyu Wang and Oscar Vafik realized. And then they said, and the third one should be in here. And if we look, there's a feature there. We had noticed it, but we sort of discounted it. But that's where the third Van Hoff singularity is, and actually that's where two Fermi surfaces of slightly different size merge into one. And if we take the quantum oscillations and take Fourier transform, we see that there are two frequencies to the left of here, and that abruptly jumps to one frequency to the right. So the Van Hoff singularity, there is no Van Hoff singularity there. 1D Fermi surface, yes.
All right, let's take David again. Again, $2. They come heading for lunch, right? Yeah. Say good. She does. So yeah, the last speaker of the morning is Senthil. He's going to talk about fractional hyperemesis, quantum anomalous solving Moire graphene.
All right, it's been wonderful to be here. Thanks to the organizers for putting together the real March meeting program. I'm actually not even going to the fake March meeting next week, but I've learned a tremendous amount being here. A lot of good discussions with people. Yeah, so I'm going to talk about this topic, and the work was done with Jihwan Dong and Adesh Patri, who been absolutely wonderful to work with, really brilliant young people. Um, yeah, so you heard a lot about Moire materials, including that we should not capitalize Moire, though Steve violated that in his own talk. So I'm nevertheless, I prepared my slides before and I took Andrei seriously and tried to give a review for the first 10 minutes. Hopefully it's not too elementary, but we'll see. We'll go from there. So I think everyone in this room, because you're here, probably agrees that this was a huge landmark development in condensed matter physics. It's a beautiful thing, probably one of the most beautiful things that happened in physics in the last 40, 50 years, at least to my mind. That we're all condensed matter physicists, so we'll agree. So you all know this, and physics is that you have electrons in 2 dimensions in a strong magnetic field, and you form Landau levels, and the electrons have Coulomb interaction, they see some disorder, and it gives the physics of the gap quantum Hall states. And at the fractions, you get excitations with fractional statistics, nicely demonstrated very recently by Mike, and fractional charge. So it's cool stuff, right? So it's cool enough that we want to try to explore it in many other platforms, in many other circumstances. And that's the topic of the talk. We can ask about the possibility of a quantum Hall effect without a magnetic field. And that was done theoretically a long time ago. And the idea was that if you fill an integer number of Chern bands, you get an integer quantum Hall effect. And this was observed first in magnetically doped topological insulator films. Now, it's also possible that the time reversal that needs to be broken to get a quantum Hall effect may be broken spontaneously by the system. So you get ferromagnetism, the system develops its own ferromagnetism, and then that enables the formation of a Chern band. So in that circumstance, this phenomenon is called an integer quantum anomalous Hall effect, or oftentimes just a quantum anomalous Hall effect. And the kind of experimental data that one should see, David already showed this, his work, which led to this eventual discovery in Andrei Young's group. This is in a TBG material. And this is the kind of data that I'll flash in the first part of the talk. So I want to emphasize the phenomenology, right? The phenomenology, the zeroth order part, one part of the package is that there is hysteretic transport as you sweep a magnetic field through zero, right? You see that in the longitudinal resistance, see that in the Hall resistance, right? The forward and backward sweeps give you different answers for this hysteresis. Now, beyond the coercive field, the Hall resistivity is quantized, in this case to h over e squared, about 1 part in 1,000. Right? So this is the phenomenon of the integer quantum anomalous Hall effect. It's routinely seen in many, many different systems, including in multiple Moire graphene systems, Moire materials, but also in things that are not Moire. So the next logical question that one could ask is about fractional quantum Hall effect without magnetic fields. And the thing that you might contemplate is that if you, instead of fully filling a Chern band, if you fractionally fill a Chern band, perhaps you realize a fractional quantum Hall effect without magnetic fields. And this was discussed theoretically and demonstrated and numerically in toy models in many papers in 2011. Several of the papers are listed here, and the only person from this group that is currently in the audience is Andrei. It's very nice papers that raise this possibility of fractional quantum Hall effect without a magnetic field. And that's a lot of nice theory done starting 2011. But in terms of material realization, there were questions that were completely open, right? So how do you get Chern bands in real 2D material, which are flat enough that you can get correlated phenomena, right? How do you get breaking of time reversal, right? So you could again imagine explicitly breaking time reversal in some way without a magnetic field, perhaps through Floquet engineering or something like that. People have proposed ideas of that sort. But it's interesting to ask whether you can also break time reversal spontaneously and get these flat enough Chern bands. And there's one question that, I've given talks on this for several talks on this in the last few months. And there's one question that 2 or 3 people in the audience always ask me politely later. And the question is, why is any of this interesting? You know, this entire field. Well, obviously, I find it interesting. I work on it, but Andrei finds it interesting. He's worked on it for 10, 15 years. Many people have, but I think it's a question that should be addressed by those of us who find it interesting. And hopefully I'll convey some of the reasons why I think it's very cool stuff. Okay. So this rapid progress in the last few years on where to look for the zero field fractional quantum Hall effect. And the idea was to look for it in Moire materials, right? There's various Moire graphene systems that it became very clear soon after Pablo's first discoveries on TBLG that various Moire graphene systems may be good platforms for this phenomenon. So we wrote a paper early on with Pablo, led by Yohi Zhang, and it's a number of numerical papers, studying this possibility. Ahmed is somewhere in the audience, perhaps. He was here. There he is. So that's him, and this work by my group as well. And starting 2019 with this paper of Alan MacDonald, people realized that Moire transition metal dicyclogenides may also be good platforms at the right, homo PMD bilayers twisted in some range of twist angles. And Liang and Valentin is somewhere, and they've been doing beautiful work on the theory of these Moire TMDs as platforms for this phenomenon. In terms of experiments, David already mentioned the work of Amir Jacobi, where in 2021, where you see fractional quantum Hall states at low fields, not at zero fields, but at low fields. The fields are low in the sense that the flux through a unit cell is much smaller than a flux quantum, right? But it was getting there, but didn't quite make it. And the real success came just last year on twisted TMDs first from Chodong Xu and the Cornell group, and most recent, and a little bit later from Longzhu on pentalayer rhombohedral graphene. Okay, so let me give you some of the theoretical background that's needed to get into this topic. So let me start with 2 basic facts of Moire materials. First, the Moire wavelength, the superlattice wave spacing is much, much bigger than the lattice spacing. This means that in momentum space, the Moire-Brillouin zone is the size of it is a tiny fraction of the atomic Brillouin zone. And the second fact that one needs to know is that the electrons live in 2 separate valleys that are related to each other by time reversal. Right? This, of course, has been assumed by all the others. There's a correct fact that has been, the previous talks assume that everybody knows this, and I just want to emphasize that this is a true statement. Okay, so a typical situation that happens is that the Moire potential disconnects the bands in the 2 valleys, right? So you take Moire graphene, the 2 valleys are connected through the band bottom. But once you have a Moire potential, in many Moire materials, the 2 valleys are disconnected. There's a Moire band gap that opens up, and then the Chern number in each valley becomes well defined. Right? Each valley is not time reversal symmetric. Time reversal relates the 2 valleys, and the bands in each valley are separated from everything else by a band gap. So then you can talk about the Chern number in each valley. Right? So the bands may have a well-defined Chern number, but since the 2 valleys are related by time reversal, the Chern numbers must be equal and opposite. Okay, so there's the notion of a valley Chern number. The point is that you can get this kind of situation because of the way in which time reversal acts on the Moire bands. Right? There are 2 bands and they're related to each other by time reversal. So that's something, one of the things that sets the stage for this. So, I like to think of this Moire field as pre-Pablo and post-Pablo. So in the pre-Pablo era, there was actually a very nice paper which pointed out that you may get topological bands in these Moire superlattices. Right? And the example that was used was monolayer graphene aligned with hexagonal boron nitride. As David said, Pablo's group and David's group had shown that this alignment can open up a band gap at neutrality. So Levitov and his students considered the topology of the resulting block bands in the Moire superlattice. And they pointed out there are situations, depending on details, you may get bands which can have valley Chern number plus minus 1, right? Now, it turns out that the bands here are not very flat. The Moire bands are not very flat, but nevertheless, this is a first hint that Moire materials may be good places where you can get these valley Chern numbers, right? It's a demonstration and get the valley Chern numbers, and then if the bands became flat, maybe interesting things will happen, right? So now post Pablo, with the knowledge of Levitov's paper, becomes clear that you should look for it in Moire materials which have flat bands, right? So, so in this paper, we looked at a number of systems. One example that I will talk a little bit about, and which David mentioned, is Bilayer graphene aligned with boron nitride. And here it turns out you can get valley Chern numbers of either 3 or 2, depending on the depending on details. And you get this only for one sign of a perpendicular displacement field. For the other sign, you get valley Chern numbers of 0. So you can turn on and turn off the band topology in a single device. Okay. Now there's another system which where the theory came just motivated by David's experiments to look at twisted Bilayer graphene aligned with HBN. And here you get bands with Chern number plus minus 1. Twisted double Bilayer graphene, you get bands with valley Chern number 2, and so on and so forth. Right? So, and in all these systems, unlike monolayer graphene and HBN, the bands are reasonably flat. So there's a hope that this interesting quantum Hall physics can arise. Okay. So what might we expect to happen? If the bands are flat, we have to deal with interactions, right? And so one way, and this is the way the route that has been demonstrated various levels of theoretical sophistication. We can imagine that we break time reversal through interactions if the band is flat. Let me focus on an example where the total band filling is, let's say, 1, including spin and valley, right? So there's 1 electron per Moire unit cell. So then the band structure, you have a situation in which in the K valley, the up and down spins each form a band with some Chern number C. In the K prime valley, they form bands with Chern number minus C because these are valley Chern numbers. And now, if you have ferromagnetic ordering in valley and spin space, then what will happen is that these bands will split in this following manner, and the ordering will be chosen spontaneously, right? So symmetry breaking. Now, if I'm at filling of 1, then I just fill one of these bands. But since each one of these bands carries a Chern number, I'll get a quantized sigma xy. I'll get a Chern insulator. Right? So that's the mechanism, right? And this can be demonstrated. So this is the story that I'm telling you, but you can demonstrate it through various levels of calculation. Yeah.
Is it energetically advent, like, because Steve was talking about these superpositions of K and K prime. So what energetically would favor going to
right. So here you don't have so there are situations in which you want to favor those superpositions, and there are situations in which you want to favor this valley polarization. So in these systems without C2T symmetry, if you're at odd integer filling, you want to favor, and this was consistent with the phase diagram that Steve showed, even in TBLG, where at odd integer fillings, his phase was IVC plus QAH, right? So odd integer filling is important. Yeah.
Suppose that there are bands and some dispersion.
Yeah.
Does the whole band has to go below chemical potential for this?
Absolutely. To get the quantized Hall conductivity, you need an insulator first, right? Otherwise, you'll get an anomalous Hall metal, right? So that's why you need the bands to be flat enough, right? So the original proposal from Levitov, the bands weren't flat enough to expect to see this phenomenon, but in the post-Pablo world, we know how to get flat band systems, right? Okay. So this is the simple physical mechanism. Let me illustrate this with the story of rhombohedral graphene 3-layer aligned with boron nitride. So this system, so rhombohedral graphene refers to a particular stacking of the graphene layers, where the A site of the one layer sits on top of the B sites of the previous layer, and so on. We'll talk later about rhombohedral n-layer graphene, but aligned with boron nitride. But really, this class of system was pioneered by the studies of it were pioneered by Feng Wang, actually around the same time as Pablo's TBLG, at least as per the archive, with a paper that first showed that you have gate tunable insulators at partial band filling in this system. Okay. There's a lot of control, as always in these Moire materials, not enough control, but a lot more control than you might naively think, where you can apply a bottom gate, top gate, and you can control the charge density as well as apply a perpendicular displacement field. That perpendicular displacement field turns out to be a good norm. And if you use the band structure, you find there's a single isolated band per spin per valley in this system. Okay. Now, if you just study the band structure naively, right, what you find is that for one sign of D, each valley, the filtered band has Chern number plus minus 3. And I'll give you a simple understanding of this in the next 2 slides. Well, for the opposite sign of D, the valley filtered bands have Chern number 0. Right? It's the same system, and you have this electrical control by just fooling around with this electric field. You can turn on or turn off the Chern number, right? The valley Chern number, which is a cool experimental capability. There's a footnote that I'll return to in a minute. So let me give you this simple-minded way to think about what's going on. Now, many of you probably know, everybody knows that monolayer graphene has an ordinary Dirac point. And many of you probably know that bilayer graphene, AB stacked bilayer graphene, has a quadratic band touching, at least approximately, ignoring warping and other terms. So rhombohedral graphene, n-layer, a first cut description of the band structure is that it has an nth order band touching. Right? I'm going to be modified by details, but we're just trying to get some rough zeroth order understanding. So for 3-layer, you have a cubic band touching. So the Hamiltonian, there's an effective 2-band description of the 2 bands that are almost touching, where there's an off-diagonal term, which goes like k minus kx minus iky to the power na, and na will be 3 for 3-layer graphene. And the perpendicular electric field adds what I would call a mass term, a term that has the opposite sign for these 2 bands. And this is the Hamiltonian that one needs to think about. So far, no Moire potential. Now here, if you didn't have these mass terms, you have a band touching, but there's a huge Berry phase associated with that band touching point. Right? The wave functions wind around rapidly in the Brillouin zone with this structure. And opposite valleys have opposite Berry curvature. And normally they would cancel because they're connected through the bottom of the band and you get 0 Chern number. Right? So this Hamiltonian will have some Berry curvature localized near each of the 2 band touching points, which are slightly gapped by the mass. But the net Chern number of the band will be 0 because the 2 valleys are connected together by the band bottom. Now, what the Moire potential does, sorry for capitalizing, what the Moire potential does is to detach the bands in each Moire Brillouin zone from the rest of the spectrum. Right? There's a Moire band gap that opens up. So then whatever Berry curvature was localized near each valley now will contribute to the Chern number of the band in each valley, of the Moire mini band in each valley. Okay? So the Chern number of each mini band becomes well defined, and it receives a big contribution from the point at which the 2 bands were trying to touch before the electric field split them apart. Okay? Now the exact value of C depends on contributions away from the band touching point. It depends on what happens near the boundaries of the Moire Brillouin zone. But you know that these will not change as you change the displacement field. Right? So this means that there's a change in sign of the as I change the sign of the displacement field, there's a change of the Chern number in each valley by plus or minus 3. So you know that at least one of the 2 signs of D, you must have valley Chern numbers. Right? And then you can do a detailed calculation and show that the way in which this is distributed is that for one sign of D, C is 0, while it's plus minus 3 for the other sign of D. Right? So this is a simple-minded story for how you can to understand the origin of valley churn numbers in this system. In this case, in fact, with high churn number. Okay, now this then suggests that you may get a quantum anomalous Hall effect at integer filling of these bands. And the experiment was done. David showed this data. Feng Wang and David and Yunbo Zhang did the experiment. And you indeed see a quantum anomalous Hall effect with a Hall conductivity of 2e squared over h. Right? So you see a churn number 2 insulator at filling 1 of the valence band. Okay, so the real question, so this is good news. You see higher churn number quantum anomalous Hall effect, as you might expect from the naive theory. But the real question, some of you may ask, is you told us the churn number should be 3, but people are seeing churn number 2. What's going on? Right? Yeah.
I actually have a question about that. So the churn number 3 was assuming some ultraviolet completion of the K prime. You're shifting things by whatever's going on in the K prime valley, presumably. Because if I just had that Hamiltonian you wrote, it would be plus or minus 3/2.
No. So that's not a well-defined churn number. I need the Moire potential to cut it off, and then the churn number becomes well-defined, and you find churn number 3. So the Moire potential gives you that cutting off of the band. So it turns out that you can rationalize this observation by including interactions at the Hartree-Fock level, and including the remote band that people have talked about. So with Yaohe Zhang, we did a simple calculation. This is some dielectric constant, and this is the interlayer potential difference. And you see a wide region where the churn number is 3, and a wide region where the churn number is 2, and we estimated that the experiments may be somewhere in the middle of this churn number 2 region. So there's a case where interactions, all of us know that interactions can renormalize all kinds of things. So why not renormalize block functions? And in particular, why not renormalize the churn number itself? And we see that this happens. So we'll see this phenomenon recur with a vengeance in the next few slides in some of the other examples that I'm going to talk about, right? Where interactions play a crucial role in determining whether a band has churn number and what the churn number is.
So
yeah.
When you are calculating this, are you calculating the renormalization of the churn number when you're like looking at integer filling, or
looking at it?
At integer filling, or
Yeah. We're looking at filling nu equals 1 specifically in this calculation. Yeah, that's right. Okay. So now let me talk about, so all that was a quick review of the integer quantum anomalous Hall effect in Moire's graphene specifically. Now let me talk about the fractional quantum anomalous Hall effect. Right. So this, of course, has been mentioned a few times. The big discovery is in the last few months, first by Xiaodong Chu, and just showing the transport data in twisted MOTE2. This is at filling 2/3, and as I promised, you see hysteresis, and beyond the coercive field, you see quantized or XY at the right value, right? And this evidence at 3/5 as well. It's also seen by other groups. One of which is published, and the Cornell group has seen the same data. So the phenomenon exists. Different groups see it, right? So and it's a big deal, right? And it's now theory support by all these names that I mentioned before. Again, Liang and Valentin or somewhere in the audience. So I'm not going to talk much more about this system. As far as, I mean, experts can correct me, but I think the theory is in pretty good shape, right? Instead, no, all right, you guys can find it out. I don't have skin in the game.
Finding out is just.
You guys have that robust discussion. Just tell me where the theory lands. All right. So what I'm going to spend the remaining time talking about is the discovery of the same kind of phenomenon in 5 layers of rhombohedral graphene aligned with HBN, nearly aligned with HBN. So you have 5 layers stacked in this rhombohedral manner. And this is a discovery made by my colleague Longju 2 months back. So before I describe the data, I want to make a couple of observations about where he finds this phenomenon. Good. Yeah. So where he finds it is in the electron dope side. Sorry?
Oh, so good.
Yeah, he doesn't find it in the whole dope side. Very important. right? He finds it only in the electron dope side. And for a particular sign of the displacement field, where the conduction electrons are driven far away from the aligned HBN sample, right? So the alignment is happening here, and that's presumably where the Moire potential sits, but the conduction electrons are sitting here, right? And so he has a phase diagram, and there's a robust mu equals 1 state that is seen. Again, you see hysteresis, and beyond the coercive field, you see quantized RHY of H over E squared. And it also sees a number of fractional quantum Hall states, in fact, 6 of them so far at 0 field. I won't go through this, but just to let me just emphasize that perhaps as you might expect, graphene is supposed to be a better material than PMD. You see many more quantum Hall states. Again, a lot of dust needs to settle in the data, but the zero thought, I think it's going in the direction of seeing many more states. Okay, so I said this is a surprise. So let me now explain why this is a surprise. So unlike in twisted MOT2, where free electron band theory predicts mu equals 1, that you have churn bands, and all you need is valley polarization to get the churn insulator. Here, if you do free electron band theory, at mu equals 1, even if only a single valley is occupied, you get a metal. You don't get an insulator. Right? So you don't get this integer quantum anomalous Hall state at mu equals 1. Within band theory, even if you assume valley polarization, instead you get some messy band structure like this. Right? I'm showing data from this paper that we wrote, where many of our conclusions are very similar to these other papers. There's further papers in the field. And actually, Andrei, my feeling is that we actually agree quite a bit with Andrei, though of course he likes to emphasize the points in his agreement.
It's important to emphasize we're in disagreement, otherwise we just agree.
I know. But we should start from what we agree on, then go to things we disagree on.
I agree.
All right. Good. So what is the physics? This means that we have to think harder about the physics in this system, right? We can't just, even the integer quantum Hall state, we need to understand as a many body phenomenon beyond the previous mechanism that I described earlier in the talk for how to get the integer quantum Hall state, which is just valley polarization of bands with valley churn number. That's not the story here, right? So the players in this system are the following. If you don't have any Moire, any alignment with HBN, you get so there's the band structure. You get a nearly flat dispersion once you turn on a displacement field, and there is Berry curvature in the band, just like in this ABC example that I mentioned before. And if you plot that Berry curvature, and I just added the below zone of the lattice, of the Moire lattice, if the Moire potential existed, just to see where the Berry curvature exists. And it's more or less hugging the boundary of the first below zone. Right? There's a lot of Berry curvature in the band. Of course, there's Coulomb interaction, and there's a weak Moire potential because the Moire potential sits here and the conduction electrons are sitting at the other end. Right? So those are the ingredients in the physics. And we have to model all these in some sensible manner and be able to say something intelligent about what's going on in the system. So we take inspiration from ancient thinkers, right? Some of you may have heard of this poet. And this, I think, is a really important guiding principle for me. It's what physicists often call a spherical cow, right? So I'm going to follow this inspiration and say that I'm going to commit a lot of sins, ignore a lot of things that perhaps in the long run will make quantitative differences. I want to see how many sins I can get away with and still capture the right physics as seen in the experiments. I want a first cut understanding of what's going on. That's my goal in life.
Then you'll repent.
And then I can repent. I'll ask for forgiveness later. Right? Okay. So one of the things we'll do, and I'll return to this later, is that we'll treat interactions in Hartree-Fock. And I'll explain why it's a bigger sin, probably a bigger sin here than in other problems, maybe. But anyway, let's start with Hartree-Fock. And so Coulomb, what we find is that Coulomb interactions, perhaps together with this Moire potential, enable an insulating state at nu equals 1. Right? So this is the band structure, the Hartree-Fock band structure for the conduction band. And this is what we find. We get this nearly flat isolated band, and you look at the Berry curvature and you look at its turn number, you get turn number 1, and this is within each value. And you can verify within Hartree-Fock that the bands or spin and valley polarized at this filling. Okay. So the conclusion is that even the integer quantum anomalous Hall state in this system is actually a fascinating many-body state. Right? Can I take a couple of minutes? Or all right, very good. All right, so let's hold it there. All right, so that's maybe the punchline of the physics that I'm confident completely that as a field we can be completely confident about. That in this system, even the integer quantum Hall effect, to enable the valley churn numbers, you need strong interactions, right? Now, there's a lot you can say about where you get this interaction-induced churn band. So there's a plot of where you get this churn number 1. There's a plot of the bandwidth, and there's a plot of the global gap. So this region in parameter space, there's the dielectric constant, and there's the interlayer potential difference. There's this region where you get a well-isolated band that is flat, that's nearly flat, has churn number 1, and has something that is maybe a good encouragement to find a fractional quantum Hall state. It has what's called a reasonable, it has a reasonable values of what's the quantum geometry in this system. So this explains, I think, this is my first better understanding of the experimental observation of the integer quantum Hall state in this system. And it sets the stage to understand the observation of the fractional quantum Hall state. So, so we did a numerical exact diagonalization, as did these other papers, for partial filling. And this is one of the sins that I'm going to try to get away with, as Andrei already pointed out. We indeed use this Hartree-Fock churn number 1 band. In our defense, we confessed our sins in our paper, right? And so you can do numerical calculations of the kind that Andrei was doing in 2011, and it works. Right? At 2/3 filling, you get you can demonstrate the fractional churn insulating state. You can look at other fillings as well, but this to account for this partial filling, the approximate treatment is to change the effective dielectric constant. Right now, this approximation is going to get worse and worse as you go to lower and lower fillings. And we said that this is something people should look at in the future. So I was glad to learn that Andrei has been looking at it in the future. All right, very good. So let me conclude by talking about this crucial question. I think the really important zeroth order question here is to understand the integer quantum Hall state. Right? Without that, I think it's premature to talk about the fractions. Right? So what is the physics of the formation of this nearly flat isolated churn band? Now, I gave you Hartree-Fock information, but we had to go beyond that. So within our calculations, there's a hint. If you look at the layer occupation, right, it turns out that most of the charge, I don't have numbers here, this is the momentum resolved occupation, but most of the charge is actually sitting in the 2 layers that are furthest away from the aligned HBM, right, which suggests that the Moire potential must have a very weak effect. So how should we understand this interaction-induced churn insulator? Now, within Hartree-Fock theory, you can look at it by turning off the Moire potential completely. After all, Moire is weak. So what happens? And you get a very similar band structure, and with churn number and so on. Right? So of course, if you don't have the Moire, you have continuous translation symmetry. Then the Hartree-Fock calculation is spontaneously breaking this continuous translation symmetry, right? Which then means that you can interpret the result of the Hartree-Fock calculation as a Hall crystal, which is another name for a Wigner crystal, which has a quantized Hall conductivity. Okay. So in the Moire system, what you then have is a Hall crystal that's spinned by the periodic Moire potential, which is commensurate with the crystal. Okay. And of course, there'll be competing many body states. There's a Fermi liquid, there's the Hall crystal, there's also an ordinary Wigner crystal, and all of these will be perturbed by the Moire potential. So I think these are again the players in determining the many body physics of the system. It's the competition between these three phases in the presence of the Moire potential. Right? And I think the people in the field more or less agree on this. There is some discrepancy here, which is going to be part of the robust discussion Andrei and I are planning. All right. So let me skip this slide. So there's some simple understanding one can give of the origin of the churn band. Let me conclude by making contact with the talks in the very first session of this conference, which I was actually very delighted to hear. Now, the biggest sin everybody in the field has made so far is to do Hartree Fock, right? All the other sins are really minor sins compared to this huge sin that we're all committing, okay? So why is that such a big sin? You know, it's often not such a big sin. I think in TBLG, so what Steve Simon was doing at integer filling is not as much of a sin as it is in this system, okay? So the point is this: if you take the ordinary electron gas, you know, we're talking about systems now with a weak Moire potential, right? So let's, and the last slide I was talking about systems with no Moire potential. So let's forget the Moire potential. So then we're talking about some continuum electron gas with some weird dispersion, Berry curvature. And let's compare with the ordinary electron gas. In the ordinary electron gas, you know, it's a famous result that Hartree Fock severely overestimates the stability of the Wigner crystal. You know, the Wigner crystal occurs at an orders of 2, while as many people mentioned in the first session, the true Wigner crystal occurs when orders is about 30, right? And furthermore, you can look, this paper has been flashed a number of times. You can look at the energy difference between the ferrofluid and the ferrocrystal, right? And if you convert this into actual numbers, energy difference you find is 0.1 millielectron volt per particle in a system where the actual energies are, you know, 100 or more millielectron volts. So it's a really, really tiny energy difference. And the real picture is that the real reason for this tiny energy difference is that the Fermi liquid looks like a crystal at short distance in time. So this is what Bilayer was calling the nearly frozen Fermi liquid. You know, that we understand is what's going on in, say, Gellium, right? And we expect a similar situation in TBG. So in Hartree Fock, you know, at the small value of the Coulomb interaction, one finds this crystal, but the true crystal transition of the crystal presumably occurs at a much larger value of the Coulomb interaction, right? And you know, the sin that one will be making is probably comparable to the sin one makes here, right? But the thing that saves us last minute, you can have the $2. So I do want to end on this note. You know, the precise phase diagram, we can either go to experiments, which may be hard, or try to do serious many-body calculations beyond Hartree Fock. I think that's the first thing as a community that I would like to learn about before we have other arguments, right? And one of the things that we learned from this weak stabilization energy of the liquid compared to the solid is that even a very, very weak Moire potential should stabilize the crystal over the liquid, right? Because the crystal gains commensuration energy, it already has the order parameter. So you apply a potential, it's going to gain energy that's linear in the strength of the potential. The Fermi liquid will gain energy at quadratic order in the strength of the potential. So one expects a phase diagram that looks like this. So you may be sitting here, but you may need an unreasonably small strength of Moire potential to push you into the insulating state that one finds, into the incompressible insulating state. So I call this a Moire stabilized or Hall crystal. And it's conceivable that the pentalayer graphene is sitting somewhere here, and maybe you can tune parameters to go here, but maybe not, right? I think this may well be the true state of affairs, and we won't know till we do a lot more experiments. And this the big uncertainty to me right now in interpreting what's going on, right? So I should stop, but let me say that the same thing predicts in 4 and 6 layer as well. But let me just put up my summary and stop.
So I totally agree with you that
as you given the talk, we agree on way more than we disagree. My point is that out of the 4 papers that are out, ours didn't touch the fractional state. Out of the 4 papers that tried to touch the fractional state, there's papers with the title, The Theory of. And then what these papers do is basically bias the state, as you admit right now.
No, let me say one thing. Andrei, I need to say one thing before we continue.
Just let me make sure I make my point. It's very, very good for the community to make sure that we are clear on what's understood and what's not understood.
Yeah.
Fractional state is certainly not understood, and writing papers with the title, The Theory of Fractional, can maybe create a false a hint that everything is understood. Do you see my point?
Right, so good. So the paper Andrei is referring to, there are actually 2 papers, but but the specific paper you're talking about, it says theory of, is my paper. So it's only appropriate to have this discussion.
Hopkins paper also, there's many papers.
Anyway. In any case, my point of view is that you have to start somewhere. And I think
you shouldn't bias the system. If you fractionally fill the band that you get the Chern number at filling 1 at 1/3, and it's got a Chern number, you're bound to get basically an FCI state. This was right. We have to make unbiased calculations. Otherwise, we claim everything is understood when it's not.
No, the claim is never that everything is understood. It's this first cut understanding. No, it's a difference between. I don't think anybody should write the first paper in the field saying they've understood everything that is there to say about a system. Okay. I think that's just so obvious that it shouldn't be discussed.
We agree.
Go to the other Andrei.
My question will be much more simple. It's about the second part.
This question was simple.
So continue. About your wonderful proposal. So as far as I understand, what you are saying is that let's forget for a second about Moire. Let's consider a system as is. And even for the system, you are saying, despite that, yes, it can be flat top, flat bottom of the band, but bandwidth is vol.
Yeah.
You are still saying that interactions are comparable to substantially modify the structure of the system.
Within Hartley-Fock.
Yeah, within Hartley-Fock.
Yeah.
There are systems besides the ones that you mentioned. For example, BVG.
BBG?
Bernard bilayer graphene.
Yeah. Mm-hmm.
Or
yeah.
Are you saying that even for this system, which I guess for some part of the community are thought to be metals and reasonably well-defined metals, are you saying that even for this system, correlations effects are strong?
Right, so good. So certainly correlation effects are strong in BBG, right? That even though it's over a wide range of displacement field is just a metal. Now you can look within the scope of this Hartley-Fock type calculation. And as you increase the number of layers, so BBG is the n equals 2 member of this n-layer rhombohedral graphene family. As you increase the number of layers, the amount of displacement field that you need to reach this kind of state, without Moire, right, becomes lower. So it's, n equals 2, you need a humongous displacement field. N equals 3, you need smaller. N equals 4, even smaller, and so on and so forth. Now, super high displacement fields you can't apply in practice. Things will break down, right? So in the range of displacement fields where BBG has been studied so far, that you don't, even within Hartley-Fock, you don't expect this kind of physics, right? But the bigger issue, I think, is that Hartley-Fock is probably a very poor guide. It gives you some indication of what may happen, but we should take, without the Moire, so another way to say it is that I take the Hartley-Fock more seriously if I know that I have a crystal. Right? So without the Moire, I don't know. I may be sitting here. Am I sitting here, or am I, sitting somewhere? I don't know. Right? And these two are likely to be very, very different from each other, like in Gilliam.
So there was a tremendous amount of progress in the field, discovering the integer anomalous Hall effect on the fractional one.
Mm-hmm.
Can you speculate about the non-abelian anyons and whether this might be a good platform for them as opposed to the regular Hall effect? For
sure.
Topological quantum computation. It's
okay.
not a question just to Senthil, it's an experimental.
Yeah, so let me put it this way, right? For many years, people wanted to find this sort of fractional Chern and Slater, fractional quantum anomalous, or whatever, right? And then it's found in MOT2, and now it's found in pentalayer graphene. I'm confident that there'll be many other systems where it'll be found in as t bigger than 0. And one or other of these platforms, people will see a non-abelian state. It'd be shocking if people didn't. And so let's be optimistic, right? I don't know anything about topological quantum computing. This may not be the good platform. That may be a sales pitch for funding agencies, but.
Yeah, so Senthil, when you showed the case without the Moire and you said Berry curvature is present roughly where you'd end up with the Brion zone produced by the Moire. What happens as you change the twist angle between the boronitride and the?
Yeah, very good, very good question. So as you change the twist angle, here, of course, this is without any Moire potential, but with the Moire lattice. So as you change the twist angle, you change the size of the Moire below zone. So as you go to larger twist angles, right, the below zone expands, and you now start getting some Berry curvature into the first below zone. So then the system is more primed to become a Chern insulator. But the region where you get this ring of Berry curvature is also the region where you transition from the flat portion of the dispersion to the highly dispersing portion of the dispersion. So there's a trade-off, right? And we don't know what will happen, and if people will get lucky, and then there'll be interesting things that happen. It's a sweet spot for interesting things to happen.
That's question. Oh, sorry, you have another one?
Question.
But first.
So about this point that you can understand this Chern insulator turning off the Moire potential as a Wigner crystal, maybe one.
Within Hartley Fork, I want to,
But let me ask you this one point. So how to understand the period, because the period matches the Moire unit cell, right? So if it's just without Moire, how does it pick the period to be?
Right. So the period will be set by the density, right? But then if you then turn on the Moire potential, you lock to the.
But the periods could be very different, right? How does it know that it has to have the same period that
it won't. In general, it won't. And then there's a competition between, so you have a Chern 1, a Hall crystal and a Wigner crystal, let's say, right? Both with they're competing with each other, right? And they're at some density that for Moire might correspond, the Moire lattice filling might correspond to 0.8 or something, 0.9, right? So then the Moire potential wants to have a certain below zone. This Hartley Fork solution that you're finding wants to have a different below zone, right? Then there's a competition between the commensuration energy of the Hall crystal versus the commensuration energy of the Wigner crystal versus states which have the wrong lattice spacing compared to the Moire potential, right? And addressing those kinds of competitions, you can try to do it within Hartley Fork, but I'm not sure I trust Hartley Fork at that level.
But within the spirit of what you said, this distance that they have is selected by the Coulomb force.
Absolutely, yeah. So it's selected by the density.
Sure, but by the interactions that they have even without Moire potential. So when you turn on the Moire potential, that if it's weak, how is it going to squeeze the electrons closer?
No. So if the deviation of the density from the preferred density is small, then you gain commensuration energy. So what you may prefer to do is to adjust the lattice constant, so to gain commensuration energy and accommodate the different density by having some freely floating vacancies in the crystal. This is analogous to what Ilya briefly mentioned about self-doping, vacancies and interstitials forming a metallic state, even in the ordinary electronic Wigner crystal in Gillium. Right? You might have that, but to address any of those things, it's energetics, right? Clearly, conceptually, you could imagine that happening, that it likes to form a crystal at the wrong density and have some interstitials, have some vacancies floating around. Right? Now, does it really want to do that, or is that energetically a crazy thing to imagine? So we need a good handle on energetics, right? You can try to address it in Hartley Fork, but one shouldn't do that.
All right, we're going to go for the very last
So, as you know very well, there's another interaction scheme, right? This is projection to the conduction bank.
Yeah.
As I tune the gap lower.
Yeah.
Then this projection to conduction bank is
Right.
suddenly there's another interaction scheme.
Yes.
That interaction scheme, you can get the lattice actually mattering, and this is something that, you know, we.
I'm well aware of your paper.
How do you think we can, Liang pointed out also, how do you think we can differentiate between, well, both schemes?
Right, very good. So let me, that's an excellent question, which I wondered a lot about after your paper appeared. And, you know, as you discussed in your paper for this average scheme, which may be legitimate at lower displacement field, what the experimental is using, but let's just take that scheme for what it's worth.
At lower displacement field, certainly the projection
Exactly.
conduction band cannot be true.
Sure, obviously, but let's just take it for the displacement field that Long is using. Now, as your paper finds, the nature of the alignment with HBN matters a lot, right? One alignment, you get chur number 1, for the other, you get chur number 0. And the region where you get chur number 1 is small, right? And
comparable to the.
now,
we can talk about it.
But let me make contact with something that David said, right? In this, so you have to ask how robust this phenomenon is in experiments, right? To date, Long has 100% success rate. You know,
one sample.
No, the published paper reports 2 devices.
Cut from the same sample, right? So there's also sample. So 100%. All right.
No, but he has 2 other devices where he see. So far he's made 4 devices. Each and every one of them show this phenomenon.
You guys paying for that?
Yeah.
We're gonna go back at 1:40, so be fast.
Yeah, regular time, as we were supposed to start.
Yeah,
no, I mean, obviously, it's different.
you expect 50%